recording, that's fine. You
Okay.
record it for
Oh,
those people who are not available, but you should be available because we are taking the real time attendance and it will be counted towards the eligibility criteria to appear in the examination. So you make sure that you are right here right now in the actual time. ठीक है ना वो आप make sure
okay.
कर लें.
Okay, sir. Okay.
अच्छा, matrix methods now again flexibility, force method, and the stiffness and displacement method. So again flexibility method we discussed. So it should be now in the back of your mind what we were doing in the flexibility method. Now flexibility method again, now revision of this one. In this method, redundant constraints are removed and corresponding redundant actions, force or movements are placed. An equation of compatibility of deformation is written in terms of these redundants and the corresponding displacements. The redundants are determined from these simultaneous equations. Equations of statics are then used for calculation of designed internal actions. In this method, actions are treated as basic unknowns. Now, let me now know if you have any difficulty with this definition or with all these things which we are going through. So I'll clarify. CR, do you see any difficulty?
No, sir.
Redundant constraints, from where they are coming from the statical indeterminacy. So you need to know about the statical indeterminacy. Redundant constraints we identify, we remove them and we replace them by the redundant actions. When we remove the supports, what happens? We get displacement there, which should not be there. So we are having a compatibility problem now. As a standard procedure, what we do, we apply a unit load and find out how much is the flexibility coefficient. And when we multiply this by the actual load, which is needed to bring it back to its position, so that is our actual load. But now we need to find out from this compatibility equations, simultaneous equations. Now, in these simultaneous equations, if you see, we have four parameters. One was the DRS, one was the DRL, one was the F, and one was the AR. So F you can find out, DRS you can find out, DRL you can find out from the given conditions, and then the only unknown is the AR. So this way you can find out the AR by solution of these simultaneous equations. And once we find out this one, then we can find out the member and actions from the equations. Now, stiffness or displacement method. In this method of analysis, the equilibrium equations are written. Now, if you see the comparison, when we go to the comparison, you will see all these things. But in case of the force method, what we were doing, we were writing the compatibility equation, but here we will be writing the equilibrium equations by expressing the unknown giant displacements in terms of loads by using load displacement relations. So equilibrium equation is coming here. The unknown giant displacements, there we were having the unknown actions, but here now we are having the unknown displacements, which is the degree of freedom of the structure, are calculated by solving equilibrium equations. So here we solve the simultaneous equilibrium equations. Displacement method of analysis is preferred to computer implementation. It's a very organized method. Now, if you remember, in case of the flexibility, we were having so many choices for a structure to make it statically determinate, but here everybody will be having only one choice. The same way you will be making, you all will be making the structure kinematically determinate. And when we get to that stage, we will be discussing it. So this is more organized. That is why this is the preferred method for implementation of the computer. Now, if you see this SAFE or SAFE or ETAP, whatever structural software we have there that are based on the stiffness method. Now, what is stiffness now? Flexibility. If you recall flexibility was the displacement reduced by unit action. This is now the other way around here. Stiffness of a member It is measure of resistance to deformation. And how we define it? The stiffness of a member is defined as the force which is to be applied at some point to produce a unit displacement. Force per unit displacement when all other displacements are restrained to be zero. Now, how we write its equation? If a member which behaves elastically is subjected to a varying axial tensile force or load W as shown in figure 5, which is going to follow on the next slide, and a graph is drawn of load versus displacement. Load we will now represent by this W and displacement with the delta. The result will be a straight line. Why a straight line? Because it is elastically behaving. This material is elastically behaving. As shown in figure 5.2, the slope of this line is called stiffness. So simply the slope of this line is stiffness. So now if we come to the next slide, on the left side, you see an axial member, axially loaded with W. Now, as W increases, the delta increases. How we show it on the graph now, along the x-axis, we draw the displacement. Along the y-axis, we draw the W. So now at W, we have delta displacement, but when it is 2W, so it is becoming 2 delta. It is proportional. Now, slope of this line, which will be simply vertical divided by this horizontal, it will be simply this angle theta, which is tangent theta will be equal to W divided by delta. And this is the definition of the stiffness matrix, which is simply the slope of this straight line. So mathematically, it can be expressed as S is equal to W divided by delta. So this is now the definition of the stiffness. In other words, stiffness is the force required at a certain point to cause a unit displacement at that point. So first, a force are required to produce a unit displacement. Equation 5.1 can be written in the following form. So if we reorganize this W will become equal to S delta, where W is equal to force at a particular point, S is equal to stiffness, and in some books you will find this stiffness notation instead of S, it is represented by K. And delta is equal to this unit displacement of the particular point. Now, in orange, you can see this note now. The above equation relates the force and displacement at a single point. This can be extended for the development of a relation between load and displacement for more than one point on a structure. Here now, relation between flexibility and stiffness. What is the relation between this flexibility and stiffness? We take here a spring which is stretched by a force A. So A is for the action. And under this application of action, it is tensile in nature. It extends by a distance D now. Now, as the action is increasing, this D is increasing. So means A is directly proportional to D, or D is directly proportional to A, where A stands for action and D stands for displacement. This was the case in case of the extension, tensile forces. In case of the compression, you can see now this behavior on the right hand side. A is applied and it is compressed by D. Again, A is directly proportional to D, or D is directly proportional to A. Since the spring is linearly elastic, that is, actions are directly proportional to displacement, so we can write D is directly proportional to A, or D is equal to FA, or F is equal to D over A. So displacement produced by a unit action, which was the definition of the flexibility coefficient. So here we can now say where F is the flexibility of a spring. Now, vice versa, if we now write this A is directly proportional to D. So A is equal to SD. To remove this constant of proportionality, we need to put this some constant here, or S is equal to A divided by D, where S is called stiffness of spring. And what is the definition of this S now? Action required to produce this unit displacement. Now from equation B, in previous slide, A is equal to ST. Also from equation A, we have D is equal to FA. So here what I am going to do now, in this equation A, instead of this A, we will put ST. So when we put this ST, we now D is going to cancel with this D1. So on the left hand side, we have 1, which is here now. So 1 is equal to Fs, or from here we say now F is equal to 1 over S, or S is equal to 1 over F. So what is the conclusion from here? From here now, it is clear that flexibility and stiffness are the reciprocal of each other. Now, with this much discussion, you should be able to now produce now this relation that flexibility and stiffness are reciprocal to each, they are reciprocal of each other. So you should be able to derive this relation. Kinematic indeterminacy, already we talked about the statical indeterminacy. Now coming to the kinematic indeterminacy. Degree of kinematic indeterminacy is the number of unconstrained degree of freedom, means displacements. You will go to the joints, and at the joints you will be finding out the capability, like how much it can move. Now your movement can be rotation, your movement can be translation. It can be in the horizontal direction, it can be in the vertical direction. And remember, whenever you have reaction at a joint, so means if it is having the capability to react the so what it is reacting now, it is reacting the displacement, it is restraining the displacement. So when you have a reaction, you will not have freedom in that direction. So means in that direction, the degree of kinematic indeterminacy will be 0. Now, in kinematic indeterminacy, we measure the total number of degree of freedom possible at a joint's freedom to move now. A structure is said to be kinematically indeterminate if the displacement components of its joints cannot be determined by compatibility conditions alone. Simple example, if I give you, we have a fixed end and fixed end beam. At both ends, we have fixed end beam. Now, what is the property of fixed end beam? In fixed support, we don't have the capability to move in the horizontal direction, in the vertical direction, and rotation also. We don't have any rotation. Why? Because we have vertical reaction, we have horizontal reaction, and we have rotation. So means we have all these possible 3 reactions. So it means it is not allowing any kind of displacement. If we take example of the hinge support, in hinge support, it can stop the vertical displacement because of having the vertical reaction. It can stop the horizontal displacement because of having the horizontal reaction. But at hinge, the moment is 0, means it is allowing the rotation now. So the kinematic indeterminacy in case of the hinge, it is 1 now, and that 1 is coming from the free rotation because of not having the moment resisting capability at that point. Roller support, if we talk about roller support, it is lying on the horizontal surface. It means it can now apply the vertical reaction. So vertical reaction means now translation in the vertical reaction, it can stop, it cannot allow in the vertical direction. Now, what about the horizontal and the rotation? Horizontal displacement, it can allow, and rotation also it can allow. So means at roller support, we have 2 degrees of kinematic indeterminacy. One is translation and one is rotation. What about now, let's say we have a cantilever beam, one end is fixed, but the other end is free now, and it is a 2-dimensional member. At the free end, if you think about, we have vertical translation. When the beam is coming down, so it will be coming in the horizontal direction also a little bit towards the support now. So it means we can have horizontal displacement also there. And at that free end, it will be rotating also. So at free joint where we don't have any support, we have 3 degrees of kinematic indeterminacies. And we'll be discussing this with each specific case now in the following slides. Now, kinematic indeterminacy for plane structures, now two-dimensional structures. So let's now talk about this one. Fixed support gives 3 reactions. So I hope you agree with these 3 reactions. One is moment and 2 are the vertical and horizontal reactions. So this is how we get these 3 reactions. One moment and 2 forces. Hence, degree of freedom at fixed support is 0. CR, do you take my this statement now?
Yes, sir.
क्लियर राइट मोमेंट अगर मोमेंट है वहां पे तो मतलब क्या है कि वहां पे आपका रोटेशन नहीं होगा अगर दो फोर्सेस है आपका वर्टिकल और हॉरिजॉन्टल डायरेक्शन है तो उसी डायरेक्शन में ये आपका ट्रांसलेशन अलाउ नहीं करेंगे तो यही तो 3 पॉसिबिलिटीज है वहां सपोर्ट्स पे अगर वो रिस्ट्रेंड आप कर रहे हैं सो इट मींस that support is fully restrained, it is not allowing any movement, so it means it is a kinematically determinate point. Second bullet now, hinge gives 2 reactions, both forces and no moment reaction. Hence, degree of freedom at hinge is 1, and that is rotation. We just talked about this one, that it is a moment is going to be 0 at hinge means it cannot resist the rotation now. So it cannot resist means there will be rotation. When there is rotation, so it means that is our degree of freedom. And that is the kinematic indeterminacy of the problem. So at hinge, we have 1 degree of kinematic indeterminacy, which is rotation. Next bullet, roller gives 1 reaction in translation direction. Hence, degree of freedom at roller is 2. One is rotation and one is translation. Now, for a 2-dimension rigid joint are free and the number of degree of freedom at a joint is 3. It will be rotation and 2 will be translation. So if it is a frame rigid joint, it will be allowing moment. Although the moment of one member is going to be same of the other member, so it will be rotating but by the same amount. So 1 rotation, and then we will be having 2 translations, 1 vertical and 1 horizontal. And similarly is the case in case of the free joint. For internal hinge, the degree of freedom is 4 now, 2 rotational and 2 translation. So you will have to remember this. If we have an internal hinge, so it will be allowing 2 rotation and 2 translation. So kinematic indeterminacy will be 4 degrees, 2 rotations and 2 translation. Next slide, we will be discussing 3-dimensional now case. So kinematic indeterminacy for 3-dimensional. Fixed support gives 6 reactions and 6 reactions means 3 movements and 3 translations. 3 will be in 3 dimensions. So hence degree of freedom at fixed support is 0. In case of the hinge support, hinge will be allowing now movements in all 3 directions. So means 3 rotations in all directions. These are becoming your unknown joint displacements. It can be taking the vertical, horizontal, and then in the z direction also the translation, the reaction. So it means it is not allowing any translation, but it can allow the rotation, 3 possible rotations, and 3 possible, these translation will be restrained. Next, we have roller gives 1 reaction in translation, 1 in 1 direction, hence degree of freedom at roller is 5. 3 rotations and 2 translations we will have as unknown. So it means 5 degrees of kinematic indeterminacy in case of the three-dimensional structures. For a three-dimensional rigid joint or free joint, again, we have 6 degrees of kinematic indeterminacy, and those will be 3 rotations and 3 translations. For internal hinge, the degree of freedom is now becoming 9 now, and it will be 6 rotations and 3 translations. Now, some equation we need to now develop. Most of the time, remember, when you are deciding about the kinematic indeterminacy, so the preferred way is to just do it by observation, because this is very quickly. You don't need to apply any equation. So most of the time we do it by observation. We'll discuss it in the following examples. But generally for a coplanar, you can use this equation, kinematic indeterminacy, which is denoted by Ki. It is equal to 3j minus r plus I, where j is equal to number of joints, r is equal to number of reactions, and I is the number of internal hinges. Now, sometimes we ignore the axial effects. Why we are ignoring? Because those are negligible. So if we ignore the axial deformation, then the kinematic indeterminacy will decrease. Now, why we are ignoring the axial? So again, I give you the answer, because they are negligible. Kinematic indeterminacy after ignoring the axial deformation is equal to, it is kinematic indeterminacy is equal to 3j minus r plus I, which is coming from this top equation. But now you need to take out the axial effects now, so which is minus number of members. So by subtracting the number of members, now you can ignore the axial effects and you can reduce the kinematic indeterminacy. Why we are reducing it? Because its effect is negligible, and if you ignore them, you now end up with less kinematic indeterminacy, less number of now simultaneous equation you will be needing, less solution difficulties you will be now facing, and quickly you can solve the problems then with less efforts. Now here kinematic indeterminacy, how we find out. In the top, this white portion, now you see a cantilever beam. Left end is fixed support, and on the right end we have a free end. So at the fixed support, this 0, it is showing the number of kinematic indeterminacy here. Why? Because it is having the capability to resist displacement in each direction, vertical, horizontal, as well as moment. So here it is 0. And at the right, which is a free end, here we show this 3, means it can have this vertical displacement, it can have horizontal, and it can have rotation also. It is going to rotate this way. So if you see here, it will have rotation, it will have horizontal distance, as well as it will have vertical also. So this 3 is coming from this one. So kinematic indeterminacy, now if we look at the joint conditions 0 plus 3, which is written here, it is now kinematically indeterminate to 3 degree, this cantilever. Now, if we ignore the axial effect, so we are taking out the number of members now here. So if you see, so ignoring axial effects, so 3 was total minus 1. This is the, because of this one member. So this is becoming now 2 degrees indeterminate. Or if we use the equations directly, so equation was 3j minus, let me go to the previous slide. So it was 3j minus r, right, plus I. So this is 3j. So 2 joints we have, this left joint and right joint. Minus restraints, how many we have? We have 3 restraints here at the fixed support, vertical, horizontal, and then the moment also. So this 3 is coming from there. And if we ignore the axial effect, so it was 3j minus r minus the number of members. So this is 2. So if you see, this 2 is matching this 2, and this 3 is matching with this 3. This was from observation, and this was with the help of the equation. Coming to the second one now, at the left we have hinge support and at the right we have roller support. Here we have 1 degree of freedom now where this one is written. And what is that degree of freedom? It is rotation here at the hinge support. And at the roller support now, it can allow this translation in the horizontal direction and it can allow the rotation also. Only we don't have the translation in the vertical direction because it can offer resistance in the vertical direction. So here we have two kinematic indeterminacy. One is this horizontal translation and one is rotation. And here only one rotation we have. So it means 1 plus 2, it is 3 degrees indeterminate. So simply by observation, you can write 1 is coming from here, 2 coming from here. This is 3 degrees indeterminate. Ignoring the axial effects, again, one member you need to subtract. So this is becoming 2 degrees indeterminate. If you want to go by the equation, now most of the time people forget the equation. So if you forget the equation, this is the option. You go by the observation. Now, so J is equal to 2. This left hinge support joint and the roller support joint are reactions 3. Which one are those 3 reactions? One vertical at this left support, one horizontal at this, and then one vertical here. So this is how we get these 3 reactions. So this is 3J minus R. It is giving you 3, which is exactly what we did by observation. And then ignoring the axial effects, so minus number of members we are. So this is equal to 2. So again, if you see this 2 is matching with this 2 and 3 is matching with this 3. So means our observation and our equation, they are working perfectly. Coming to this 2 span now.
एक्सक्यूज मी सर
Yeah.
सर ये फिगर 1 में जो j इज इक्वल टू 2 किस सर इसकी एक एंड तो फ्री है जॉइंट तो नहीं है वो
ना तो फ्री अगर होता है ना तो उसको भी हम जॉइंट लेते हैं ना. जॉइंट मींस इट कैन बी फ्री एंड इट कैन बी हैविंग सपोर्ट आल्सो. ठीक है. तो मेंबर के दो मेंबर मतलब अगर एक पॉइंट आप लेते हैं ना, सो दैट इज अ पॉइंट दैट इज नॉट अ मेंबर. मेंबर के लिए क्या डेफिनेशन है? इट शुड बी हैविंग 2 एंड्स नाउ. तो इसका वन एंड क्या है? इट इज फिक्स सपोर्ट, एट द अदर एंड इट इज फ्री नाउ. ठीक
सही है.
अच्छा ठीक है. फिर आते हैं ये 2 स्पैन प्रॉब्लम पे. दिस इज हैविंग 2 स्पैन एंड 3 supports now. Left support is hinge support and then we have roller support, then we have roller support. अब अगर मैं देख लूं तो यहाँ पे at the left support we have 1 degree of freedom which is rotation. And in the middle support we have rotation as well as we have now translation in the horizontal direction. When the horizontal direction, when we are taking effects of the axial effects when we are considering. Similarly, when we come to the right support, so again it can give rotation and it can give translation also in the horizontal direction. So 1, 2, and 2. Now these are the degrees of freedom now at each one of these joints. So if we add them up, it is coming 5. So 5 is written here. 1 plus 2 plus 2. Now, if it is given, now you ignore the axial effect. So 1 member and 2 members we need to subtract. So this is becoming 3 degrees indeterminate. And what are those 3 degrees now? It will be rotation at 1, rotation at 2, and rotation at this final support, which is to the right. We are ignoring the axial translation in the middle support and at the right support. So only rotations we are considering. Why rotations? Because the axial effect, the bending stresses will be more in case of the beams. By using the equation now, joints we have 3. Reactions we have 4, 2 from the left support, 1 and 1 from the middle and right support each. So this is becoming 5 degrees, which is matching with this one. Ignoring the axial effects, again it is coming 3 degrees. Similarly, if we ignore the axial effects in the first one, so it is giving us 2 degrees now indeterminacy. Which one will be those 2? It will be the vertical translation and it will be the rotation here. The axial will become 0 in the horizontal direction. Similarly, here if we ignore the axial effect, means in the direction of the member we are ignoring. So it means rotation at left support and rotation at the right support. Those are becoming our unknown quantities, and those are those 2 degrees of kinematic indeterminacy. Coming to now the last one, it is having 1 at the hinge support, which is rotation here. Then 4 at the this internal hinge. Now, why this is 4 here at this point? This is the question now. Look, if this hinge, if I bring it to here, I make it a general case. Let's this 1/4 portion I'm moving here. Can you see my cursor, CR?
Yes, sir.
See, you see, right? Instead of this now, I bring it here. So when it deflect, how it is going to deflect now? It is going to deflect here, this hinge, and from here it is going to come here now. Now what will happen now? This left side rotation is not going to be equal to the right side rotation. So at this hinge, we will be having 2 different kind of rotations now. This is why we have 2 independent rotations. If it is in the middle, you can say, oh, left rotation is going to be to the right rotation. But what happens if it is unsymmetrical? Unsymmetrical rotation is what? It is vertical divided by horizontal. So vertical is going to be the same, but horizontal distance is not going to be the same. So it means theta is going to be different. When theta is different, it means we have 2 independent rotations now. So that is why at the hinge we have 2 unknown rotations and 2 unknowns translations. So this is now becoming 4 degree. This is why we call it 4 degree. Again, at the roller, if we take axial effects into consideration, it is 2 degrees. So 1 plus 4 plus 2, it is becoming 7 degrees, which is written here. If we ignore the axial effects, so it means 7 minus 2, it is 5 degrees now. So 5 degrees now, ignoring here with the help of the equation, you can find out, and we are getting the same result, 7 and 5. In case of the now rigid joint frames, if we see the first one, it is 1 bay and 1-story frame now. At the left, we have a fixed support. At the right, we have a fixed support. The top joints, those are free now. So from here, we have 0 degree. From here, we have 0 degree. Here, we will be having 3 degrees. And here, we will be having 3 degrees. So 3 degrees and 3 degrees, if we consider the axial effects, this is becoming 6 degrees indeterminate problem. One from this left top and one from the right top. So 3 from here and 3 from here we are getting. Means it is 6 degrees total indeterminate problem. So J, if we use the equation, number of joints, we have 4, 1, 2, 3, 4. And number of reactions, if we see 3 reactions here, 3 reactions here, so we have 6 reactions. So 3J minus R, it is becoming 6 degrees. This is total 6 degrees. But if we ignore the axial effects, means it cannot move in this direction, it cannot move in this direction, it cannot now in this direction because of this member. So we need to take out these 3 now because of these 3 members. So it means ignoring axial effects, this will become 3 degrees now. So this is becoming 3 degrees kinematic indeterminate problem. Similarly, if we come here now, so 1 degree from here we have, 3 degrees from here we have, 4 degrees from here, 3 degrees from here, 3 degrees from here, and 2 degrees from this one. So by observation, you can add them up. 1 plus 3, 4 plus 4, 8 plus 3, 12 plus 3. So how much we have? This is, you can add them up and see if it is coming equal to 16 degrees. Ignoring the axial effects, we have 1, 2, 3, 4, 5 members we need to take out. So this is becoming 16 minus 5. It is equal to 11. It should be 11, not 5. This one. So, Faisal, are you there? Okay, he is not, but he can make the correction. And similarly here, number of joints you can count 1, 2, 3, 4, 5, 6, 7. So these are this 7 number of reactions. 3 from here, 2 from here, 3 from here, 2 from here, 1 from here. Now we have. So you can take out this store, and if you remove the axial deformation again here, you need to make some for this. So you can come up with the remaining kinematical indeterminacy. Now after knowing the kinematic indeterminacy now, general procedure of stiffness method, how we go with the stiffness method now. This method is also called displacement method. Why displacement method? Because the joint now freedom, we consider that as our unknown, and we are interested in finding out that displacement. So that is why it is known as displacement method. In case of the flexibility, which was also known as force method, because the actions were unknown, the redundant actions. So that is why it was known with the method of force method also. In this method, the degree of kinematic indeterminacy is determined. So first you need to find out the kinematic indeterminacy. And the displacement components are identified. So you go after the free joints now, you identify them and you label them. A coordinate is assigned to each independent displacement component. वहां पे हम क्या करते थे, and that if you remember, we redundant actions we identified and we labeled them as AR1, AR2, AR3, and so on. Here the unknown quantities will be the displacement, so we will designate them by D1, D2, and D3, Dn, and so on. So AR is replacing D now here in this module now, which is the stiffness method. Are the redundant displacements at location 1, 2, 3, and n location. If all the redundant displacements are restrained, now what we do to make the structure now, which is kinematically indeterminate, we need to make it determinate now. Now, what was the parallel there in case of the flexibility method? We need to make the structure statically determinate. How it was done? We removed the redundant actions. We removed the redundant actions, and the structure was known as basic determinate structure or primary structure. Now, how we are going to make this structure now kinematically determinate? We will make it kinematically determinate by locking it, by not allowing the displacement which is there now. So how can we do it? We need to now restrain it. कैसे आप restrain करेंगे? Let's we have a hinge support. Hinge support is allowing rotation. अब आप कैसे इसको करेंगे कि it should not be allowing the rotation. You just put a fixed support there. हिंज को आप क्या करें? आप फिक्स सपोर्ट पे रिप्लेस करें. अगर रोलर सपोर्ट है आपका, आप कैसे करेंगे? इसमें वन ट्रांसलेशन जो आपका आ रहा है और एक रोटेशन जो आपका आ रहा है, इसको आप कैसे करेंगे रिस्ट्रेंट? अगेन यू पुट अ फिक्स सपोर्ट देयर. अगर फ्री जॉइंट है किसी कहीं पे आपका जो कि 2 ट्रांसलेशन और एक रोटेशन अलाउ कर रहा है, इसको आप रिस्ट्रेंट कैसे करेंगे? वहां पे भी आप फिक्स सपोर्ट रखते हैं. So if all the restrained displacements are restrained, all the redundant displacements are restrained, the resultant structure is known as restrained structure. वहां पे क्या कहते थे हम? रिलीज स्ट्रक्चर कहते थे. यहाँ पे हम restrained structure कहेंगे. और बेसिक काइनेमेटिक डिटरमिनेंट स्ट्रक्चर, वहां पे बेसिक स्टैटिकल डिटरमिनेंट स्ट्रक्चर था, यहाँ पे बेसिक काइनेमेटिक डिटरमिनेंट स्ट्रक्चर, अब इसको हम कहेंगे. Now, कैसे अब करेंगे इसको? How we proceed further? It first requires satisfying equilibrium equations for the structure. अब equilibrium, अब क्या होगा? Hinge support पे आपका moment आपका 0 आ रहा है. At hinge support we have 0 मोमेंट। लेकिन जब आप वहां पे फिक्स लगाएंगे, फिक्स आप क्यों लगाएंगे? क्योंकि आप रोटेशन को स्टॉप करेंगे। जब आप इसको फिक्स करेंगे तो वहां पे क्या हो जाएगा? आपका मोमेंट आ जाएगा। तो अभी सवाल पैदा हो रहा है कि ओरिजिनल स्ट्रक्चर में आपका मोमेंट नहीं है और अभी आप फिक्स करने से वहां पे मोमेंट ला रहे हैं, तो आपका क्या है? वहां पे आपका कंपेटिबिलिटी कंडीशन डिस्टर्ब हो रहा था, यहाँ पे अभी आपका इक्विलिब्रियम कंडीशन डिस्टर्ब हो रहा है। इंस्टेड ऑफ जीरो नाउ यू आर गेटिंग सम मोमेंट नाउ। तो अब इस मोमेंट को क्या करेंगे? अपोजिट डायरेक्शन में हम मोमेंट लगा के इसको जीरो पे लाएंगे, विच इज द ओरिजिनल कंडीशन, एंड दैट वे वी जेनरेट इक्विलिब्रियम इक्वेशन। वहां पे कंपेटिबिलिटी कंडीशन को हम सेटिस्फाई कर रहे थे, यहाँ पे हम इक्विलिब्रियम कंडीशन को सेटिस्फाई करेंगे। Now to do this, the unknown displacements are written in terms of the loads by using the load displacement relation. Load displacement relation हम लिखेंगे। Then these equations are solved for the unknown displacements. Once the displacements are obtained, वहां पे क्या था? When the redundant actions are obtained, तो क्या है? The unknown loads are determined from the compatibility equations using the load displacement relation for n independent displacement. अब यहाँ पे आप सिमिलरिटी देखें प्रीवियस में एंड दिस मॉड्यूल, वहां पे डी आर एस था, यहाँ पे क्या आ रहा है? ए डी वन। डी आर एस वन इज रिप्लेस्ड बाय ए डी वन। डी आर एस क्या था? इट वाज द precondition at the support displacement at the precondition displacement due to precondition at the support or at the redundant location था। यहाँ पे आपका क्या होगा? एक्शन करस्पॉन्डिंग टू द डिस्प्लेसेबल जॉइंट होगा। एक्शन को आप देखेंगे कि डिस्प्लेसेबल जॉइंट की जगह पे आपका कोई प्री कंडीशन है कि नहीं, जिस जहां पे एक्शन लगा हुआ है वहां पे आप डिस्प्लेसमेंट को आप देख रहे थे करस्पॉन्डिंग टू द अननोन रिडंडेंट एक्शन। ADL1 क्या होगा? दिस इज रिप्लेसिंग द DRL नाउ। तो ADL अगेन आपका एक्शन होगा एट द डिस्प्लेसेबल जॉइंट इन द बेसिक काइनेमेटिक डिटर्मिनेंट स्ट्रक्चर ड्यू टू लोड। यहाँ पे आप क्या देखेंगे? वहां पे आप डिस्प्लेसमेंट को कैलकुलेट कर रहे थे, यहाँ पे आप क्या करेंगे? मेंबर एंड एक्शन आप कैलकुलेट करेंगे। इंस्टेड ऑफ द डिस्प्लेसमेंट यू विल बी कैलकुलेटिंग द एक्शन नाउ corresponding to the displaceable joint due to the actual loads. वहां पे आप F11 कैलकुलेट कर रहे थे, यहाँ पे S11 कैलकुलेट करेंगे। S11 कैसे कैलकुलेट करेंगे? It will be the force required to produce a unit displacement. So क्या करेंगे हम? We apply a unit displacement and find out the corresponding actions. D1 क्या है? वहां पे AR1 था, यहाँ पे आपका अननोन जॉइंट डिस्प्लेसमेंट आ गया। Similarly S12, D2 and so on. Similarly AD2 for the multiple now degree of freedom you can generate these simultaneous equations. So now if we want to write this in the matrix notation form, this will become AD, this will become ADL, and this will become stiffness coefficient, and here we have the unknown joint displacements. If we want to write this in the condensed form, so AD is equal to ADL plus S times T. यहाँ पे अब आप कंपैरिजन कर रहे हैं। AD, this is taking the place of the DRS. ADL, it is taking the place of DRL now. S, it is taking the place of the F, and this D, it is taking the place of the AR now. So you can see the resemblance and the similarity in these equations. और रीअरेंज कर ले, अब AD आप मालूम कर सकते हैं, ADL भी आप मालूम कर सकते हैं, S भी आप मालूम कर सकते हैं, D is unknown, so D को रीअरेंज कर ले, so AD minus ADL जो कि यहाँ पे लिखा हुआ है, and then this will become divided here by S, divided here by S, so this becomes S inverse here. So D is equal to S times AD minus ADL. This is now the final format of this one. Now again, now the definition of these various terms now. AD, ये AD क्या है? Look, this is external actions corresponding to the displacement joint. वहां पे DRS क्या था? It was the कंडीशन जो कि आपका डिस्प्लेसमेंट था corresponding to the redundant action. यहाँ पे क्या है corresponding to the redundant joint displacement है this AD and it is action ना वहाँ पे displacement था यहाँ पे आप action को देखेंगे. Similarly ADL क्या है it is action again वहाँ पे DRL क्या था that was the displacement but here now ADL it is the action corresponding to this displacement joints in the restraint structure due to the applied loads, fixed end actions. D KI, this is the unknown joint displacements, which are your kinematic indeterminacy. S KI, it is the stiffness coefficient, which is displacement per unit force. Displacement per unit. No, this is the displacement per unit force. It is the definition of the flexibility matrix. Faisal, are you there? So, okay, we'll make this correction, but stiffness, it is the force required to produce unit displacement. Now, stepwise solution procedure using stiffness method. The following steps must be followed while solving a structure using stiffness method. First step will make the structure kinematically determinate. And how we make this kinematically determinate? We just restrain the joints. No displacement is allowed at the joint. That is, select the redundant joint displacements. Construct the AD. अब क्या करते हैं? Once we restrain the joint now, we take example of the hinge support. तो hinge support पे आप क्या restrain करेंगे? आप rotation को restrain करेंगे. आपको rotation के corresponding आप देखेंगे कि वहां पे कई moment तो नहीं लगा हुआ. If we have a moment there corresponding to that rotation, that is becoming your component of the AD matrix. So that way we construct our AD matrix from the actions corresponding to the redundant joint displacements. Right? So this is now the point from where you can construct your AD matrix, and most of the time you can do it by observation. You look at what you are locking there, what you are restraining there, what kind of now displacement you are restraining there, and corresponding to that you look after the action. If action is there, corresponding action is there, you include that in the AD matrix. If no corresponding action is there, we just put 0 there in front of the AD. Next, now step number 2, apply the actual external loads on the basic kinematic determinate structure and find the actions at the location of redundant actions. Compute fixed end actions. This will generate ADL matrix. Now, when we restrain the structure, fixed end actions will be produced here. And corresponding to now whatever you locked, whatever kind of displacement you restrained, you go and find out the fixed end actions here. And that actions you include in the ADL matrix. Sign you decide depending on the sign of rotation or translation. If your corresponding reaction is in the direction of the translation, you take it positive. Otherwise, you take it negative. Step number 3, apply the redundant joint displacements on the, now we are coming after the generation of the stiffness matrix. So stiffness matrix में flexibility पे हम क्या करते थे? वहाँ पे unit action हम corresponding to the redundant action apply करते थे. यहाँ पे क्या करेंगे? हम unit displacement apply करेंगे corresponding to the displaceable joint. तो क्या करते हैं? Apply the redundant joint displacement on the basic kinematic determinate structure. To standardize now the procedure, only a unit displacement is applied in the positive direction. This will generate the stiffness coefficient matrix. क्या करते हैं? We apply the unit displacement now. Because of this unit displacement, actions will be generated, fixed end actions will be generated. and corresponding to this displaceable joint आप क्या करेंगे, वही एक्शन आप लेके stiffness matrix आप generate करेंगे. So we'll be discussing this with the help of the examples. Step number 4, now we come to the equilibrium equation. Now apply equilibrium condition at the location of the redundant joint displacement to write equilibrium equations and solve solve for unknown joint displacement. So AD is equal to ADL plus S times T, or D is equal to S inverse AD minus ADL. So this way we find out the unknown joint displacements. And after this, we have the standard procedure of finding out the member end actions. And for the member end actions now, what we will have again, we will have AM is equal to AML, and that's standard equation we used to have in case of the flexibility method. AM was equal to AML plus AMR times AR, but here it will be a bit different. Now, let's start now with the help of this example. To illustrate the above mentioned procedure with the help of the general example, you are looking at a single span beam now. At A, we have a fixed support. At B, we have a roller support. And W is the UDL carried by this beam. Now, if we ignore the axial effects now, this beam is becoming 1 degree indeterminate problem. And that 1 degree is just the rotation at B. Theta B is the unknown rotation now. And that is shown here. So in this orange now to the right, in this orange color, you can see kinematic indeterminacy is equal to 1 degree. So one redundant joint displacement should be chosen. And which one is that one joint? This is rotation at D. This translation in the horizontal direction at B, we are ignoring. Why? Because we take this axial effect and this member is equal to 0. It is not going to be compressed or it is not going to be elongated because of these forces. That is negligible. If you take that one also, then it is becoming 2 degrees indeterminate. So in step 1, what we do, selection of redundant joint displacement. So rotation at B is taken as independent joint displacement. So here rotation at this D we have. Now, how can we make this kinematically determinate? The only way is to provide here a fixed support. So by providing a fixed support, it was already having the capability to stop the translation in vertical direction. Because of this member, it was having to stop it in the horizontal direction. Only rotation was free. So we are locking or we are preventing only this rotation now. So here we put a fixed support. So basic kinematic determinant structure we will be looking this way now. Where this D, now if you fix it, here the moment was 0, but when you fix it here, a moment will be generated. So it means it is now violating the equilibrium condition. Initially, you don't have any moment, but when you make it kinematically determinate, you will be having some moment value here. This is the basic. Now, this structure we call a restraint structure. This is restraint structure. Here now, the basic kinematic determinate structure. Now, if we go to the previous one now, here if somebody is asking you, now you tell me how much will be AD matrix. So here I don't see any externally applied moment here now at this joint B, which is corresponding to this D now. So means our AD matrix is going to be equal to 0 because we don't have any externally applied moment here. That's the moment here applied. It is in the counterclockwise direction and it is 1 foot now. So if we are choosing this clockwise as our positive direction for this rotation, the action now, corresponding action is in the counterclockwise direction. So means our AD1 matrix will become equal to minus 1 foot now because of the opposite direction of this moment. Now, Here now, step 2, now we expose now this basic kinematic determinant structure under the actual load, which was W. This is going to be the deflected shape of this structure. No rotation here, no rotation here. So means now we will be having some moment here because of this fixity of the support. Originally, it was not there. So now whatever action is produced here, this fixed end action, whatever is coming here, that will make our ADL matrix. And we have fixed equations for such kind of conditions now. What will be the moment here? It will be WL squared divided by 12. So very quickly you can find out this ADL component. So this will become your ADL, which will be equal to MB. Now, but in original structure, we don't have any moment there because it was a roller support which cannot resist the moment now. So क्या करेंगे now? We need to bring it now to the same condition. कैसे करेंगे? At here we should be applying now moment in such a way so that the summation of this one and this one, it should put this system in equilibrium now. So first what we do, we apply a unit rotation now and we generate the stiffness matrix. And then we multiply this by the actual MB to just to cancel this effect now. So हम क्या करते हैं? We apply this unit rotation now. And because of this unit rotation, what will happen? And actions will be generated. How we find out those actions, we'll discuss this in a while. But right now you should be knowing the concept. It is exactly the same. What we did in the flexibility method, we released now the redundant action here, and because of that, we ran into the compatibility problem because we were having the displacement here. Now, what we are having instead of the displacement, we are having now the action problem here. It is not matching the initial condition. Here, what was the procedure? Now we apply the unit load multiplied by whatever load is required to bring back it to its position. अब यहाँ पे हम क्या करेंगे? We apply a rotation, unit rotation multiplied by the actual now movement, so that the moment here it comes into equilibrium now. So after that now, after generating of the stiffness matrix multiplied by this corresponding now displacement, this is because of the unit displacement, so we need to multiply by the whatever actual displacement we have here in order to create the actual moments, and that moments will be now taking care of this moment produced here. And this way we can put this system in equilibrium. So AD is equal to AD is coming from the previous slide. ADL will be coming from here and S will be coming from here. Now, how much should be the actual displacement now, which should match the actual roller condition? So that is still unknown. We put it here now. Now AD will be known, ADL will be known, S will be known. The only unknown will be D now. So what we can do now, we can find out this D. So apply equilibrium condition at the location of the redundant giant displacement and solve the matrices to compute the values of unknown giant displacement. So after solving these simultaneous equations, we find out the unknown giant displacements. Once the unknown giant displacements are known, very easily we can find out now the various now reactions, actions, whatever you want, the internal actions you want to find. The rest of the displacements, everything you can find out. Now, comparison now between the flexibility and stiffness method. Flexibility method, what we do first, we determine the statical indeterminacy. Stiffness method में हम क्या करते हैं? Determine the kinematic indeterminacy. Flexibility method, choose the redundant actions to obtain the BDS. Basic determinant structure. Choose the redundant actions to obtain the basic determinant structure. यहाँ पे हम क्या करते हैं? Choose the redundant giant displacement. यहाँ पे redundant actions का था, यहाँ पे giant displacement to obtain the restraint structure. यहाँ पे basic determinant या release structure था, यहाँ पे हम क्या करते हैं? Restraint structure. And compute the DRS values. यहाँ पे हम DRS values हम करते थे, यहाँ पे हम क्या करेंगे? We will be computing the AD values. So you can see the process here. Here the unknown was the reaction, vertical reaction. And this is now that redundant action. यहाँ पे क्या है unknown? This is the rotation here. So here this D, we label it as a D now. So this is the unknown giant displacement. Second step, now we assign coordinates to the chosen redundant. ये आपके coordinates हो गए R1, R2 जो भी जितने भी आ रहे हैं. यहाँ पे क्या है D जो है ना आपने लेबल कर. After this now आपका AD मैट्रिक्स जो है वो जनरेट हो गया. After this now we expose or we subject the basic determinate structure to the actual loads. Process is the same. लेकिन फ्लेक्सिबिलिटी में हम क्या करते थे, हम DRL मैट्रिक्स जनरेट करते थे. वहां पे हम डिस्प्लेसमेंट्स में हम थे इंटरेस्टेड. यहाँ पे आप क्या करेंगे, हम एक्शंस जो है ना वो find out करेंगे in order to create the ADL matrix. So in the release structure, compute the displacement, which is DRL at coordinates due to actual loads. ये क्या था corresponding, अगर आप AR का देख लें तो यही displacement हम calculate करते हैं. यहाँ पे हम क्या करेंगे, in the restraint structure compute actions ADL at the coordinates due to the loads other than those acting at the coordinates. तो यहाँ पे क्या है, उस corresponding आपका D था, तो D के corresponding आप action देखेंगे तो जो action आ रहा है वो आपका हो जाएगा ADL, which is MB in this case. So that easily you can find out your ADL matrix. Now, next step was generation of the flexibility matrix in case of the flexibility method. यहाँ पे आप क्या करेंगे, इसका parallel जो होगा, this is step number 4, not step number 3. So यहाँ पे आप stiffness matrix अब आप generate करेंगे. अब क्या था flexibility matrix का, corresponding to AR unit action हम वहाँ पे लगाते थे. यहाँ पे corresponding to the displacement हम कितना displacement apply करेंगे, unit displacement. In the release structure, compute the displacements at coordinates due to the unit redundant actions, that is construct F. यहाँ पे हम क्या करेंगे, compute the actions at the coordinates in the restraint structure due to a unit redundant displacement and construct the stiffness coefficient matrix. अब क्या था, in case of the flexibility method, we were writing the compatibility equation. This plus this is should be equal to whatever you have precondition. यहाँ पे हम क्या करेंगे, this plus this should be equal to the actions in the actual structure. So here now use compatibility conditions at the coordinates to determine the redundant. So DRS is equal to DRL plus F times AR, or AR is equal to F inverse, and it is times DRS minus DRL. And what we will do now here in the stiffness method, we will use the equilibrium condition at the coordinates to determine the independent displacement. And equation will be AD matrix will be equal to ADL matrix plus stiffness coefficient matrix times the unknown giant displacement matrix. Our D will be equal to S inverse AD minus ADL. Now you take 2 minutes and see the resemblance in these two equations. DRS AD, DRL for ADL, F, S, and AR for the D now. You see corresponding now, instead of now the displacements, we are after the actions now. And instead of the AR, we are finding out the unknown giant displacements. And similarly, the rearranged equation you can see, instead of AR, now we are finding out the displacement. Instead of inverse of the flexibility, we have inverse of the stiffness coefficient matrix. Instead of the DR, S, which was a precondition, now we have a precondition AD, action corresponding to the displaceable giant we will be looking. Instead of the DRL, we will be looking now again action corresponding to this displaceable joint in the actual loaded structure. So this is the equation. Compute member and actions, the same process which we had in case of the flexibility method. We will be having the same process in case of the stiffness method. And drawing the shear force and bending moment diagram. So here also we will be having drawing shear force. And so you can see now the comparison as well as the similarity now in these two methods. Yes, sir. See,
Excuse me, sir. We can take break, sir.
I was thinking you are going to ask me some nice question now, and now you are asking me about the break now. So let me see what is next now. So this is formulated. Okay, so what time it is now?
12:30, sir.
10:30. 10:30 or 12:30?
12:30, sir. 12:30.
12:30. Okay. So should we be back by 12:45?
Yes, sir.
15 minutes break. Okay, so you have a 15 minutes break and then we meet after 15 minutes. Okay.
Okay, sir.
Okay, take care.
Okay, sir.
Hello?
Yes, sir.
Yeah, can we start now?
Yes.
Okay, let's go now to this one. Formulate the beam shown in figure below using stiffness method. How we are going to formulate this problem now? Now, if we ignore the axial effects, so it is becoming 2 degrees kinematically indeterminate problem. And which one are those 2 degrees? One is theta at B and one is theta at C. How it is going to deform now? Here we don't have any rotation, so it is going to go this way and then it is going to come this way. So we have rotation at C and rotation at B as our unknown. So two independent giant displacements should be chosen. Now how we declare our unknown giant displacements here, you can see this is D1 now, rotation corresponding to B, and this is rotation at C now. So this is D2 now. So this we D2. And in clockwise, we assume them as positive. Again, it is assumption now. You can take clockwise or you can take counterclockwise. But from here now, you fix your positive direction. Now, this is the actual structure now. F corresponding to D1 FVC, we don't find any action now. No rotation, no moment is here corresponding to D1 and no moment is corresponding to D2. So this way we declare our AD1 is equal to 0 and AD2 also is equal to 0. And D1 and D2 are our unknowns. How we make this as a restraint structure? We just put a fixed support here at B. We replace this roller by a fixed support and we replace this C also by a fixed support. Everybody will be doing it at the same way. You don't have any other options here. So rotation at B and C is taken as redundant giant displacements and basic kinematic determinate structure or restraint structure we will looking like this. What we are restraining here, D1 we are restraining here. What we are restraining here, D2 we are restraining here. And from this now, when we restrain this, so D1 correspondingly in the actual structure, we are looking for the corresponding action, and corresponding to the D2 also, we are looking for the corresponding action, which are the moments in this case, which are 0. So we complete this AD1, AD2 is equal to 0, 0. Now, next we will be now generating the ADL matrix. So ADL matrix is this one. This is the actual structure now. At B, we make this fixed support. So now actually at the fixed support, we are now dividing this into fixed. Again, it is fixed. Fixed means again, it is a fixed support. And here again, this is now at 2. Now this coordinate, this is the fixed support now. It is under the actual loads P1 and P2. So what we do now, restraint structure is acted upon by the actual loads P1 and P2 were the actual loads pointed one. Compute the values of actions in the restraint structure. Now, because of this fixity at B and at this C, you will be having actions now, and those actions, corresponding actions, will give you your ADL matrix to the redundant locations. Now, this will generate ADL matrix, and this A is from the actions. This is the displaceable joint, and it is because of the load ADL. ADL1, which will be here, it will be the algebraic sum of these corresponding moments now. Moment, why moment we are taking? Because rotation was unknown. If it was a, let's say, translation, so corresponding to the translation, which will be settlement here, then you will be taking this reaction as the corresponding action. ADL1, it is moment in the restraint structure under the actual loads corresponding to the redundant joint displacement 1. And ADL2 will be the moment in the restraint structure under the actual loads corresponding to the redundant joint displacement 2. Next now, this way you generate your this ADL1 and ADL2 value and put them in the matrix form. Now we have generated AD and ADL matrix. The remaining is the stiffness coefficient matrix. Now, in step number 3, we come and the primary structure is acted upon by a unit value of D, and computation of stiffness coefficients value in the basic kinematic determinant structure corresponding to the redundant joint displacement location. Turn by turn, we will be applying now the unit displacement now. D1 was a rotation at B. So corresponding to that, we will be applying now the unit displacement. First, a unit rotation is applied at location 1 and prevent it at location 2. So what we do, this fixed support for a while, we convert this into a hinge support and we apply a unit rotation. This one is for the unit rotation. And this way we find out the corresponding actions generated. Now, there is a very nice relation now. If you give now rotation at one end, how much will be the action generated at that end, which is near to the rotation where we are applying the rotation, that will be known as the near end, and the other end, which will be far, that will be known as the far end. Now, when rotation is applied, so at the near end, the action, which is the moment generated, will be 4EI theta divided by L, length of that particular span now. If we take the left span, so this L will be the left and this span. And if it is the right one, if we are taking, so this L will be this right one L. Now 4EI theta divided by L, this will be the action generated. From where this is coming, again, we will be discussing now the conjugate beam method, from where we get these actions, how these actions are produced. Now at the far end, this moment will now shift in the same direction now. If you see here, the left one, it was produced in the clockwise direction. Why is clockwise direction? Because the rotation given was in the clockwise direction. So the action generated at the near end is in the same direction as that of the rotation. Its magnitude is 4 EI theta divided by L. And at the far end, it is shifted in the same direction. It was clockwise, so this is clockwise. Here, if you see, it is clockwise, so this one is also clockwise. And it is shifted by the half amount. The carryover factor is half here. So instead of 4 EI, we have 2 EI theta divided by L. Now, the left span, now if you want to put this in equilibrium, here we have rotation 4 EI theta divided by L. At the left, we have 2 EI theta divided by L. So this will now cause rotation of the span now. To put this in equilibrium, we need to balance this by the opposite couple now. So how the opposite couple, this magnitude is calculated. It will be the summation of this unbalanced moment, which is 4 plus 2. So 6 EI theta divided by L, divided by this span, which is L. So it will be equal to 6 EI theta divided by L square. So this is the balancing couple. Now summation of vertical forces will be equal to 0. So this is how summation of vertical forces. This was a clockwise moment now generated because of this unit rotation, and it is balanced by this couple 6 EI theta divided by L square. Similarly, it is the situation for the right side span now. 4 EI theta. At the far end, it is becoming 2 EI theta. Now, and the balancing couple for the right span, again, it was clockwise, so the balancing couple will be equal to counterclockwise. Its magnitude will be equal to 6 EI theta divided by L square. From where this 6 is coming, it is because of this unbalanced moment addition, 6 plus 2. So 6 EI theta divided by L, this is the unbalanced moment. How we find out this force divided by LV? Because moment is going to be balanced by the moment. So what is the moment of this couple? It will be the force multiplied by this distance, which is L. So again, you can find out these reactions. S11, again, the subscript as we did in case of the F11 and F21, it is the same concept. One is the location, and second subscript, it is coming from the cause where you are applying the unit displacement. So here now we are applying the unit displacement at this one location. So whatever values, member actions we find out, that will become our S11, and for here it will become S at 2 due to 1. So this will become S21. Now what will be the S11 value? If here at this joint where this we have coordinate 1, the corresponding actions to the displacement. What was the displacement? Unknown displacement was the rotation. So to the rotation, we have corresponding action moments. Which one moments are now corresponding? This 4EI over L and this 4EI over L. Both are in the clockwise direction. So we will be adding, algebraically adding them up. So your S11 value will become equal to 4 plus 4 EI theta divided by L. So this will be 8 EI theta divided by L. What will be S21? This is again corresponding to the D2 now, which was rotation at C now, theta C. So 2 EI theta divided by L. Simply this will become your S21 now. That easily you can find out your these stiffness coefficient matrices. Second, now what we do now is coming the turn of applying a unit displacement corresponding to theta D2 now. So here now, if you see, we are applying a unit rotation. At the near end, 4 EI theta divided by L. At the far end, 2 EI theta by L. This is now having full capacity to restrain to take this moment. It is not going to distribute this to the left support now. So 2 EI theta divided by L. How we balance it? Again, by this balancing couple, it was in the clockwise direction, this unbalanced movement. So we need to balance this by the counterclockwise. 6 I theta again by the summation of this divided by L. So 6 I theta by L. Now, what will be the designation of here? This stiffness. This stiffness will be 2EI theta divided by L plus 0. From this side, we have 0. And its designation will be S12, S at 1 due to 2 now. So this is S12 will be equal to 2EI theta by L. And now you see 2-1 was 2EI theta by L, and 1-2 is also 2EI theta by L. And it must be matching. If it is not matching, it means something is wrong with your calculation. What will be the designation of this one? It is A2 due to 2 now. So S22, and it will be equal to 4EI theta divided by L. Here at the bottom, you can see the definition of S12 and S22. So stiffness coefficient matrix at 1 due to 2 and stiffness coefficient at 2 due to 2. Now, next, now stiffness matrix is also generated. ADL we have, AD also we have. The only unknown is now the D now. So we come to the equilibrium equation. Now we write the equilibrium equation. Since it is 2 degrees indeterminate problem, so the stiffness matrix is going to be 2 by 2. These are the two unknowns. This is a column vector again, 2 by 1, and this D is also 2 by 1. And from here D we have, now these are the unknowns D1 and D2 now. So D is equal to S inverse D. Next we come and find out, once the displacements are found, we come to step number 5, which is the computation of the member and actions. Now, member and actions, how we are going to find out the member and actions now? Again, everything now, each information you have now. So what we need to do now to put all these informations now in an order, the corresponding information, in order to find out the member and actions. Now, member and actions are the moments or shear at each point where it's going to be changed. We can find the member and actions using stiffness method when the redundant joint displacements are known. After finding out the redundant joint displacements, you are in a position now to find out these member and actions. Let's illustrate the procedure of finding member actions by stiffness method with the help of the above mentioned example. Again, the same example we are giving now. P1 in the left span, P2 we have in the BC span. So if member and actions are, even support reactions are required, how we find out? So let's go now. Here now, if you see D1 and D2, these were our unknown joint displacements, D1 and D2. Now, we specify the member and actions that we are interested now, shear or support reaction at A, this vertical reaction, we designate this by AM1. Just to the left of this support B, the shear is AM2. Just to the right of this support B, AM3 and AM4, and here, this is clockwise rotation. Again, remember, these are your reference now directions, and these are arbitrary. You can assume any direction, but from here onwards, these will become your positive signs now. AM6, and so if you find out AM6, AM7, again, automatically it is found. You don't need to find it out because they will be same in magnitude and opposite in direction. They will be balancing each other. But for calculation purposes, we want to see whether they are matching or not. So AMN, this is the member and action in the indeterminate structure. Which one indeterminate structure? In the kinematically indeterminate structure at different locations. N is now the numbering 1, 2, 3, and so on. So corresponding to this, now we need to pick AML values. If you remember, AM was equal to AML plus AMR times AR. Now here the equation will become AM is equal to AML. Instead of the AMR, now we will be having AMD. There was the reaction, here we have the displacement now. And instead of the times AR, it will become times D now, because we have the unknown giant displacements now. So determine the member and actions now, which is shear and moments in the restraint structure under the actually applied loads. This is the actually applied loads now. We need to find from there now AML1, AML2, AML3 as we did in case of the AML in case of the flexibility method. So these are all those corresponding values now, corresponding to the AM's values. Next now, we need to generate instead of the AMR now, here we need to generate the AMD values now. And from where it will be coming? From where we generated the stiffness coefficient matrix. So you see here now AMD11 it is corresponding to AM1, AMD21 it is corresponding to the AM2 now. From where this 2 is coming, this is coming from AM2. From where this 1 is coming, this 1 is coming from this location now, where we have this redundant, this application of the unit displacement corresponding to the redundant displacement. Similarly, AMD 3, 1, and 4, and so on. Now, next slide, it will be corresponding to 2 coordinate. Now we will be applying the unit displacement and finding out all these member and actions. So if you see here now, this theta is equal to 1 and corresponding this, now you see AMD 1, 2, 2, 2, 3, 2, 4, 2, and so on. And after this, now you have the equation. So you just plug in these values and solve it. So this will give you the unknown, these member and actions. So AM will be equal to AML times AMD times T. This is the equation. Again, you can see the similarity between the flexibility method. There it used to be AM is equal to AML plus AMR times D. Here we have AMD times D now. And how to pick these values? Here this is now slightly, here we need to correct this. This should be AMD11, AMD12 instead of AMR. Right? So R is not there. This R is going to be replaced by the D values. Next, now action. Now we said that if we give a rotation at one end, so the moment generated at that particular end will be equal to 4 EI theta divided by L. At the far end, it will be in the same direction, but half of that amount, which will be 2 EI theta divided by L. We need to balance it by the balancing couple, which will be 6 EI theta divided by L square. Right, so here now you see all this. At A, you can see a rotation is given in the clockwise direction, theta A. Because of this theta A, the action generated MA is equal to 4 EI theta A divided by L. At the far end, it will be 2 EI theta A divided by L. And the balancing couple will be 6 EI. Now, how these values are coming, so we'll prove this from the conjugate beam method now in a while. Now, class activity M is equal to use conjugate beam method. You have 10 minutes. So you can try this, but I'll give you the solution right now. Or even you can go to the 3-moment equation and you can very quickly you can do it. Now, instead of the rotation now, F at the support, if we provide a settlement now, delta A here, it is provided. If a unit rotation is applied at joint, now, if a unit translation is applied at joint A, then the moment induced in the members are shown in the figure. So instead of rotation, now what we have a vertical translation now, delta A. Now, because of this translation, what will happen? This end will try to come back to its position. So this gives you the direction of the moment produced here. And here that moment is given. Look, it is trying to come back to its position, so it means it is clockwise now. What will be the magnitude? Because of the rotation, it was 4 EI, here it is 6 EI theta divided by L square. Here it was 4 EI theta A divided by L only, but here it is 6 EI delta theta. Again, you can prove this from the this 3-moment equation or from the conjugate. At the far end, it will Hold on for a second. I got a phone call, so I'll be with you like in a minute. Hello? Walaikum salam. Sagincha. Why? Yara the class ke mata ta veli ne sangincha 2 bajo por zama class kana so hosum class kana wa. Wali so بس هغه ما وی سي سه بوغي سره خبرو کو چې دا سچويشن دی کنه هغه به ډیسایډ کوي او فعلال دی ده السلام علیکم او ارشاد خیر دی بالکل ټیک ټاک چاته دی فارورډ کو نو هولډ کړه د ما خیر وی سي سره شیر کو ما نمبر زر سره چیک کړ کنه هغه ټیکو نو بس هغه ته ما وای ما کوي بیا خو بټولې پیسې دی کنسم کې کنه دی کې به یو لیبارټي فعلال کیږي کنه نو بس هغه کوارډینیټر او چیرمنان نو تاسو کو چې سره پرایورټي دا شان دی فکس کیږي نو هغه ته ما دا کړه خو فارورډ کړی سره خو خیر مونږ خو اوس کرنټلی دا کې کتو کنه لکه نو خو په کار چې اپډیټ وو سره کنه ځکه الته ډیسیژن اخستې شو نو مطلب چې دا فیوچر د پاره چې تاسو بالکل کلیر یې چې صدا کوي کنه ټیک شو کنه دا تاسو دا کوي چې الته ډیر ځکه دی باندې ډیسیژن اخستې شي ټیک شو زب بس هغه اوس هغه به کوي فیصله Okay, sorry about the interruption. So if a unit translation now, so what happens at the near end, the end will try to come back to its position and it will be giving you the direction of the movement produced, which will be equal to 6EI delta A. Delta A is the settlement now given produced there divided by L square. At the far end, it will go in the same direction. If you see here, the movement produced was in the clockwise direction. So far end, it is also in the clockwise direction. And the magnitude is going to be the same. It is not going to be half now. So 6EI theta A divided by L square. This is very important, the very basic. You should be understanding how to fix the direction of this movement produced and what will be the magnitude. So the direction, the end will be always trying, look, if I take it to the up direction now, the delta is in the up direction. So how we fix the direction? It will be trying to come back to its position. So its direction will become counterclockwise. At the far end, it will be also counterclockwise. Its magnitude will be 6EI delta A divided by L square. If I take this, let's say here we don't have any settlement, but we have settlement here at B now. The settlement is in the downward direction. So downward direction, it will try to come back to its position. So means it will become now counterclockwise. Counterclockwise again, it will be 6EI delta B now divided by L square. At the far end, it will go in the same counterclockwise direction by the same amount. Once you know the amount of the unbalanced moment, it is very easy to find out now the amount of the couple. Now, what will be the couple? It will be summation of these unbalanced moments, which if we take this specific problem now, which is on the screen right now, so it will become 6EI delta A divided by L square plus 6EI delta A divided by L square means it is 12EI delta A divided by L square. This is the total unbalanced moment, and divided by L now, that will give you the magnitude of this balancing couple. So 12EI delta A divided by L cube divided by L square and divided by L will become L cube. Now, this is how we get this 12EI delta, and this is how we get its sign also. It was clockwise direction, so the balancing couple is going to be in the counterclockwise direction. So we found all the member and actions because of this settlement. We found all the member and actions because of the rotation also, if it is given at an end. CR, any question?
No, sir.
Clear?
Yes, sir.
because you will be using this again and again, quickly you need to find out all these values, right? So if a structure is given, a member is given, so first you need to look at the I value, whether it is 0.5i, 2i, 1i. So accordingly, you will have to put that in equation. If each settlement is given, so accordingly, you will have to incorporate the settlement length. That specific length you will be given, you will be looking at, and you will be putting that in this equation. So when we come to the real problem, after now this class, you will be having 1 week now to go through this and through each and every point. You can have a mutual discussion also. If you have any question, you can ask me then in the coming lecture, but you should be clear about all these, how these member and actions, what will be the sense of, what will be the magnitude of all these member and actions. Now, from where this MA is equal to 4 EI theta A is coming. So let's prove this now so that you have the confidence now. Prove that MA is equal to 4 EI theta A divided by L. Now, if you look at this wide screen, at the left now we have a hinge support, which is support A. At the right, we have a fixed support, which is support B now. What is happening there now? Rotation without transverse displacement of one end of a prismatic member, the other end fixed. Only we are allowing rotation at A now. So theta A, you can see here this in red. We are allowing this rotation because of this MA. And we want to now find a relation between this MA and theta A. Now, once this is found, now we can find rest of the values by using the equilibrium approach. Now, if we want to draw now a bending moment diagram for this structure now, so here we have MA. Now, MB will be generated here. This MB is arbitrary direction now. We assume this in the same clockwise direction. So what will be the moment here? It will be MA plus RA times this L if we take moment of forces here at joint B. So it will be MA plus RA times L, which is shown here at the right. So this is becoming the bending moment diagram now. In between the member, we don't have any load now, so it is going to change by a straight line. So for this given condition, this MA plus RA times L, it is actually MB now, and MB is equal to this amount. This is the bending moment diagram. What we do now in the conjugate beam, fixed support is going to be changed by a free end, and hinge is going to be replaced by the hinge now. So this is actually now the conjugate beam, and this conjugate beam, we load it with the bending moment diagram. So here we have at the left, we have MA, and at the right, we have MA plus RL. So this is the bending moment to the right. So this is the conjugate beam now corresponding to this actual structure acted upon by the M or EI diagram. Now, from equation of equilibrium, what we have, if we take, now if you see here the conjugate beam, it is shown by RA prime now. Reaction at A, or shear at this is RA prime. Now, if you find out the reaction here, what this will become now in the actual structure? Anything now. This here, if we find out the shear here, it will become the slope actually in the actual structure. Slope in the conjugate beam, the shear in the conjugate beam, it is the slope in the actual structure. And moment at a section, what that is giving us, if we find out the moment, that will give you the translation in the actual structure at that particular point. So from equilibrium equation of the conjugate beam, if we take moment about A is equal to 0, which is MA prime is equal to 0. Why 0? Because it is a hinge support. So first we take this rectangle now, which is having a magnitude of MA from here. So this will become MA times L. This will become the total load, equivalent pointed load, and it is acting at a distance of L by 2 now. So this first component, which is MA over EI, which is this vertical multiplied by the length now. So this is now the total load multiplied by L by 2. This is the moment arm. So from this rectangle, we have a moment of this first number. Then we take rectangle now. What will be the load of this rectangle? It will be half of RA times L times L, this length. This will be the equivalent load of this triangle. And how much will be the moment arm from this A? It will be 2/3 of this length now. So 2/3 of length is coming. So MA is equal to 0, MA prime is equal to 0 if we take, this is becoming the moment of this rectangle and triangle. In the next slide, what we do now, we now solve this MAEI, we take to the right and then we solve it for RA. So RA is becoming equal to minus 1.5 MA divided by L. Minus 1.5 MA divided by L. This was from the MA prime. What about the RA prime now? RA prime, how much is going to be this reaction now? It will be simply the load of this rectangle plus the load of this triangle, which will be MA divided by EI times L plus half of RAL over EI times L, which is the area of this triangle. So if we add them up, that will become equal to RA prime. So RA prime, this way we find times. Or if we now simplify this, why simplify this? RA we are going to put from equation 1 now in terms of this MA. So when we solve this, RA prime will become equal to MAL divided by 4EI. And what is this now? This is actually theta in actual structure will be equal to the reaction in conjugate, shear in conjugate. Now, slope in actual will be equal to shear in conjugate. From that relation now, instead of RA, we can say theta A from the actual. And this is MA divided. If we rearrange this, so MA is equal to 4EI theta A divided by L. So this we put that at the near end, if theta A is given, our MA is required to produce theta A now. So 4EI theta A divided by L, that we have accomplished. Now we substitute this MA value in equation 1 now. So RA will become equal to minus, and this RA will become equal to minus 6EI theta A divided by L square. So in the actual structure, we found out the reaction also, which is minus means it is in the downward direction. And remember, in balancing the moments now, unbalanced moment, we said it is 6EI theta divided by L square. Now from equilibrium, RB will be equal to 6EI theta. You can put now, you got these numbers. So from equilibrium, you can find out summation of vertical forces. And then MB very easily you can find out because you have RA, you have MA, you can take moment about B. So MB will be equal to 2EI theta A divided by 2 plus sign means it is in the same direction as that of MA. So this is 2. So we put all the 4 now. Now, if somebody is asking me that let's say some theta is given at an end of a member now, you tell me how much will be the actions generated. I'll say at the same end, which is the near end, moment will be generated in the same direction of the theta. And it will be having a magnitude of 4EI theta. Let's say A was the end, so theta A divided by L. At the far end, it will transfer by this half amount and it will be 2EI theta A divided by L. Now, the balancing couple, which will be the reactions at the support, it will be creating a balancing, means a opposite couple as that of the unbalanced moment, and its magnitude will be 6EI theta A divided by L square. So this is now how we fix the direction and how we find out the magnitude. Now, for this case now, fixed end actions, how we find out. So you should be now quickly able, for reference now, you can see here, we have in this left one, if you see in the middle of the support, in the middle of the span now, we have a load P now. L is the span, L by 2, it is telling you it is at the mid span now. So at each end, moment produced will be PL divided by 8 and PL divided by 8. You should be remembering this. If you don't remember it, the other option is you go and you analyze this by flexibility method, and you will not be having that kind of time now to analyze this and find out these support reactions. How much will be the reactions? These vertical reactions P by 2 and P by 2. If we have the same fixed ended beam, and if we have a UDL now, so it will be WL square divided by 12 and WL square divided by 12. What will be the vertical reactions? WL divided by 2 and WL divided by 2. Similarly, you can see if a couple is given in certain distance A, total span is L. So these will be the corresponding reaction at A, moment at A. This is reaction at A and moment to the right. R is for the right, and similarly, you can see these things. If it is loaded by this triangle now, increasing to the right now, so these will be the corresponding. If you have a P now at L by 3, it is not in the middle. These will be the corresponding now member and actions. Similarly, you can see here we have two P's now. So these are the common cases, and you can find out the member and actions from here. Now, one thing you need to prove now, this we did. Here you need to prove now this thing, that if we give a settlement now of delta at one end, what will be the actions generated? So like the way we did in case of the rotation, you should be able to do it for the translation. Any question? Now you can turn on your microphones and you can ask me questions.
सर जी
Yeah.
और नंबर 3 पे जरा समझ नहीं आती है, आपने पहले फिक्स किए फिर आपने कहा कि ये हिंज है तो उस पे समझ नहीं आती है। और पहला
नहीं, कौन से स्लाइड पे जाऊं मैं?
सर स्लाइड तो नोट नहीं किया था सर, क्योंकि नजर
आप देख लेना। अब आप देख सकते हैं, ये स्लाइड्स है हमारे सामने। क्वेश्चन क्या है आपका?
सर आपने कहा कि हमने पहले फिक्स किया फिर उसको हिंज बनाया।
हाँ, ये देखे ना, आप जब आप रोटेशन आप देते हैं ना, तो टर्न बाय टर्न आप देंगे ना। पहले तो आप पूरे स्ट्रक्चर को डिटर्मिनेंट बनाते हैं, लेकिन टर्न बाय टर्न आप कैसे देंगे? फर्ज करें आपका स्ट्रक्चर जो है वो 2 डिग्रीज इनडिटर्मिनेट था काइनेमेटिकली, तो पहले आप क्या करेंगे? फर्ज करें कोऑर्डिनेट 1 पे आप जो है ना रोटेशन, तो रोटेशन आप कब दे सकते हैं? जब आप इसको हिंज बना लें। बाकी कोऑर्डिनेट 2 पे आपका क्या होगा? वहां पे आपका लॉक होगा, स्टिल वहां पे आपका फिक्स सपोर्ट होगा। अब क्या करेंगे? जब आप कोऑर्डिनेट 2 पे जाएंगे, वहां पे जब अलाउ करेंगे रोटेशन, तो क्या करेंगे? आप 2 पे आप हिंज कंसिडर करके, मतलब वहां पे आप रोटेशन इज इक्वल टू 1 लिखेंगे, और 1 लोकेशन पे आप क्या करेंगे? वहां पे आप फिक्स करेंगे इसको।
सही है सर,
ठीक है ना? तो टर्न बाय टर्न आप अलाउ करेंगे। इसी तरह अगर 3 पे आप जाते हैं, 3 लोकेशन पे, तो 1 और 2 पे आप वही आप फिक्स सपोर्ट रखेंगे, लेकिन 3 पे जाके आप हिंज बना के इसको आप रोटेशन अलाउ करेंगे।
सही है सर। तो सर जो उधर जो एग्जांपल था ना सर, जो पहले एग्जांपल था, तो उसमें हमने तो टू रोलर थे, लेकिन हमने फिर भी किनेटिक इंडिटरमिनेसी सर 2 लिखा था।
हाँ, वो इसलिए लिखा था कि एक्सियल इफेक्ट्स बीम में हम नहीं ले रहे हैं ना, क्योंकि उसमें तो आप अलॉन्ग द एक्सिस आपका लोड नहीं लगा हुआ ना, तो क्या चीज उसको कंप्रेस करेगा एक्सियली?
सही है सर, फिर मूवमेंट
ठीक है, तो एक्सियल इफेक्ट्स हमने इग्नोर किए हुए थे।
सही है सर, थैंक यू सर।
एनी अदर क्वेश्चन?
Yes, sir.
अच्छा, बताएं आप।
Sir, you have said that we ignore the axial deformation. So, sir, please explain this why, sir.
अच्छा, इस तरह है एक्सियल डिफॉर्मेशन। दिस इज नॉट द फर्स्ट टाइम वी आर डूइंग इट। अगर आप पहले अगर आप जाए ना बीम में, और आप अगर जाएं उसमें रिजिड जॉइंट फ्रेम्स में फ्लेक्सिबिलिटी में जो किया हुआ था, तो कहीं पे आपने उसका ई ए लिया हुआ था? नो, वी डिड नॉट टेक एनी ई ए देयर बिकॉज वी कंसिडर दैट द एक्सियल इफेक्ट्स आर गोइंग टू बी नेग्लिजिबल। नेग्लिजिबल क्या है? अगर एक फर्ज करें आपका एक्सियल फोर्स आ रहा है after making all these calculations, let's it is coming 50 kip। अगर एक्सियल इफेक्ट्स आप इंक्लूड करते हैं, इट इज कमिंग 50 पॉइंट लेट्स से 1, तो वो पॉइंट 1 हम क्या करते हैं, वो इग्नोर कर लेते हैं, क्योंकि उसका इफेक्ट इतना नहीं आता, तो उसको हम इग्नोर कर लेते हैं। सो दैट वाज द रीजन। अगर याद पड़ रहा हो आपको, उसमें फ्लेक्सिबिलिटी मेथड रिजिड जॉइंट फ्रेम में वी जनरेटेड इक्वेशन एम एम डी एक्स डिवाइडेड बाय ई आई। वी नेवर इंक्लूडेड द ई ए इफेक्ट। ई ए इफेक्ट कहां पे हमने इंक्लूड किया? व्हेन वी वर डूइंग द ट्रस प्रॉब्लम्स। वहां पे हमने किस चीज को इग्नोर किया? हम वहां पे हमने बेंडिंग स्ट्रेसेस को इग्नोर किया। हमने कभी भी वहां पे ई आई की बात नहीं की। ठीक है ना? तो अगर आप देख ले बीम में, तो बीम में क्या है, कभी आप एक्सियल फोर्सेस आप मालूम करते हैं? नहीं। या शेयर मालूम करते हैं, और या क्या करते हैं, बेंडिंग मोमेंट। तो अगर एक्सियल वहां पे अगर शेयर है, एक्सियल फोर्सेस है नहीं, तो आप किस चीज को कंसिडर करेंगे?
Okay, sir. Thank you, sir.
अब जब हायर क्लासेस में आप जाएंगे ना, तो रिसर्च पर्पसेस के लिए फिर हम क्या करते हैं, बड़े सेंसिटिव हो जाते हैं। तो ये छोटी छोटी जो इफेक्ट आ रही है बिकॉज ऑफ द एक्सियल इफेक्ट्स, तो ये भी हम फिर वहां पे कंसिडर करते हैं। लेकिन ये आप कंसिडर करेंगे तो उससे आपका बड़ा कॉम्प्लिकेटेड हो जाएगा कैलकुलेशन इस स्टेज पे।
Okay, sir.
एनी अदर क्वेश्चन? अच्छा, if you don't have any question, again you can turn off your these microphones, or CR only he can now stay with the दिस ओपन माइक्रोफोन। ठीक है, तो अब क्या करते, थोड़ा सा मैं आपको बता दूं कि व्हाट वी नीड टू क्विकली, इट इज नॉट गोइंग टू बी, इट विल बी द डिस्कशन इन द नेक्स्ट लेक्चर नाउ। लेकिन क्या करेंगे ताकि आप उसके लिए तैयार हो। कैन यू सी माय स्क्रीन नाउ सीआर?
यस सर।
अच्छा, इसमें है ना, अब हम एक्चुअल प्रॉब्लम्स पे अभी आएंगे। एक्चुअल प्रॉब्लम्स का क्या होगा, वही आपका एक्चुअल लोड्स होगा नंबर पे, एक्चुअल स्पेन्स होंगे, ईआई की वैल्यूज होंगी, हम इसमें सेटलमेंट्स इन्वॉल्व करेंगे, 3-4 प्रॉब्लम्स करेंगे। क्या होगा, लेट्स से ये वही प्री रिक्विजिट वगैरह इसमें अभी मैं नहीं जाना चाहता, लेकिन इसमें क्या है, टू सॉल्व दिस वन, ये भी हो गया। लेकिन एक्चुअल प्रॉब्लम की तरफ आते हैं ये सारा। अब प्रॉब्लम नंबर 1 होगा। अब आप देख रहे हैं ए बी और सी पे आपके सपोर्ट्स लगे हुए, नेचर ऑफ सपोर्ट्स भी आप देख रहे हैं। अच्छा, ए बी के दरमियान अगर आप देख लें तो वर्टिकल लोड आपका लगा हुआ है 30 किप का, बी से पे आपका 20 किप का लोड लगा हुआ है, स्पेंस भी आपको दिए हुए हैं 12 फीट और 12 फीट। अब अगर आप देख लें 20 किप के लिए इसका लोकेशन नहीं है, लेकिन ये क्या है, अगर स्केच को आप देख लें, सो इट इज इन द मिडल, तो मतलब ये कि फ्रॉम द सपोर्ट सी इट इज आल्सो लाइंग एट 6 फीट मिडल पे। तो ई आई क्या है, इसका कांस्टेंट है। अब क्रॉस सेक्शनल एरिया में नहीं दे रहा, क्योंकि एक्सियल इफेक्ट्स को मैं क्या कर रहा हूँ, इग्नोर कर रहा हूँ। सो बाय डिफॉल्ट इट इज नोन, इफ आई एम नॉट गिविंग यू द क्रॉस सेक्शनल एरिया ऑफ द मेंबर, इट मींस आई एम इग्नोरिंग नाउ द एक्सियल इफेक्ट्स। और नीचे अगर आप देख लें तो काइनेमेटिक इंडिटरमिनेसी में डिक्लेयर कर रहा हूँ 2 डिग्रीज। व्हाई? within the parenthesis you see the reason also, because neglecting the axial effects, वो लिखा हुआ है वहां पे क्लियरली। अब क्या है, यहाँ पे आपके दो अननोन जॉइंट डिस्प्लेसमेंट्स कौन से होंगे, आपका थीटा एट बी एंड थीटा एट सी जो है ना, वो आपके अननोन जॉइंट डिस्प्लेसमेंट्स हो जाएंगे। तो एक्चुअल लोड्स भी आ गए, एक्चुअल स्पेन्स भी है आपके पास, और सपोर्ट कंडीशन सब कुछ है। तो इसमें D1 और D2 को आप देख रहे हैं क्लॉकवाइज, मैं एज्यूम कर रहा हूँ कि ये मेरे अननोन जॉइंट डिस्प्लेसमेंट से रिस्पॉन्डिंग टू दिस। अगर आप देख लें तो एक्सटर्नली अप्लाइड कोई भी एक्शन नहीं है, कोई भी मूवमेंट नहीं है वहां पे, तो AD1 और AD2 में 0-0 डिक्लेयर कर, D1 और D2 अननोन से हमारे पास। इसके बाद आके हम क्या करते हैं, ADL अब आप जनरेट करेंगे। तो ADL के लिए हम क्या करते हैं, पहले बेसिक काइनेमेटिक डिटरमिनेंट स्ट्रक्चर ये आपका हो गया बी और सी पे। यहाँ पे क्या था आपका अननोन, आपका D1 था विच वाज रोटेशन इन क्लॉकवाइज डायरेक्शन, सी पे क्या था रोटेशन इन द क्लॉकवाइज डायरेक्शन, इट सी दैट वाज द। अब क्या करते हैं, अब आप आके यहाँ पे मेंबर एंड एक्शंस करस्पॉन्डिंग आप मालूम कर लेते हैं। मेंबर एंड एक्शंस क्या होगा, अब देख ले जनरल इक्वेशन है, अगर पॉइंटेड लोड फिक्स्ड एंड बीम के दरमियान में पड़ा तो इसके लिए क्या इक्वेशन PL डिवाइडेड बाय 8 और PL डिवाइडेड। इसी तरह राइट के लिए क्या है P2L डिवाइडेड बाय 8, P2L डिवाइडेड बाय 8। तो यहाँ पे अगर हम वैल्यूज लगा लें तो ये आपका होगा 30 टाइम्स 12 डिवाइडेड बाय 8 जो कि 45 दे रहा है। यहाँ पे क्या होगा अगेन 45, यहाँ पे क्या होगा 20, ये 20 आ रहा है तो 20 टाइम्स L इज 12 अगेन हियर डिवाइड बाय, तो ये फिक्स्ड एंड एक्शंस। अब करस्पॉन्डिंग फिक्स्ड एंड एक्शंस को हम देखेंगे तो D1 के करस्पॉन्डिंग क्या है आपका +45 एंड -30। आप एग्री कर रहे हैं इससे कि नहीं CR?
Yes, sir.
You agree with my this statement that corresponding to D1 आपका क्या है, ये देखें ये वाला मोमेंट है आपका और ये वाला 45 और 30। 45 को मैं पॉजिटिव ले रहा हूं, क्यों पॉजिटिव ले रहा हूं, बिकॉज इट इज इन द डायरेक्शन ऑफ द assumed D1 which was clockwise। ये क्यों नेगेटिव ले रहा हूं, बिकॉज दिस इज अपोजिट टू दैट वन, वो क्या था क्लॉकवाइज, ये काउंटर क्लॉकवाइज आ रहा है। तो हमारा ADL1 कितना हो जाएगा, इट विल बी +45 -30 विच विल बी 15 के फीट। कुछ एग्री कर रहे हैं कि नहीं?
Yes, sir.
अगर नहीं कर रहे तो फिर दोबारा मैं एक्सप्लेन कर लूंगा।
No, no, sir. ठीक है।
अच्छा, anybody else if you have any problem in now calculating the ADL1, just turn on your phone and I'll clarify your question.
सर जी दोबारा बता दें जरा सर जी।
दोबारा क्या बता दूं? दोबारा
सर
ना
जी
कहें आप सर।
डायरेक्शन
This is fourth or fifth time you should, because I was explaining here from the general rotation and then I was explaining from, so this was the second time and then it may be the third time now I need to explain it. डायरेक्शन का देखें, ये देखें, अगर मैं पहले स्लाइड में चला जाऊं ना, लेट्स से दिस वाज द स्लाइड व्हिच वाज नाउ गिविंग अस द पॉजिटिव डायरेक्शन D1 एंड D2 इन द क्लॉकवाइज डायरेक्शन, ठीक है। अब इसके करस्पॉन्डिंग एक्शंस हम देखेंगे। अगर एक्शंस हमारे क्लॉकवाइज डायरेक्शन में आ रहे हैं तो हम इसको पॉजिटिव लेंगे, अगर काउंटर क्लॉकवाइज में आएंगे इसी पोजीशंस पे तो उसको हम नेगेटिव लेंगे। ठीक हो गया?
यस सर।
अच्छा ठीक है। नाउ हियर अब आप आ जाते हैं, ये वही वन कोऑर्डिनेट लोकेशन है ना जॉइंट बी का, हमने दो में स्प्लिट किया हुआ है। अगेन इट इज फिक्स्ड एंड फिक्स को आप तीन में डिवाइड करते चाहे, स्टिल इट इज फिक्स्ड वन। तो लेफ्ट स्पेन से आपका जो एक्शन आ रहा है इसका क्या है, दिस इज नाउ द डायरेक्शन ऑफ द मोमेंट, ठीक है। जो अगर इसी इक्वेशन में आप वैल्यू डाल दे, पी क्या है 30 है, इसमें एल क्या है, ये 12 फीट का स्पेन दिया हुआ है, यहाँ पे लिखा हुआ है। तो 30 मल्टीप्लाइड बाई 12 डिवाइडेड बाय 8 जो कि फिक्स है यहाँ पे, तो इससे 45 आ रहा है क्लॉकवाइज डायरेक्शन। राइट वाले स्पेन से 20 टाइम्स दिस 12 डिवाइडेड बाय 8 30 आ रहा है, लेकिन इसका डायरेक्शन अब क्या है, दिस इज काउंटर क्लॉकवाइज। ठीक हो गया। अब अलजेब्रिक सम यहाँ पे जो आएगा इसका वो आपका ADL1 होगा। अब इसमें हम साइन कैसे लोकेट करेंगे, ये 45 अगर आप देखें क्लॉकवाइज डायरेक्शन है, क्लॉकवाइज वी कंपेयर इट विद द D1 डायरेक्शन व्हिच वाज आल्सो क्लॉकवाइज, तो इसको हम पॉजिटिव लेंगे। अब 30 का काउंटर क्लॉकवाइज में आ रहा है व्हिच इज अपोजिट टू D1, तो इसको हम नेगेटिव लेंगे। तो 45 माइनस 30 ये आपका ADL1 हो जाएगा। अब आप जो क्वेश्चन पूछ रहे थे, आप मुझे ADL2 का बताएंगे, ADL2 का आपका कितना आएगा?
Sir, +30, sir.
Very good. This will be +30. Why plus? Because in the same direction as D2. Amount इसका क्या है 30। किस तरह आ रहा है P2L डिवाइडेड बाय 8 से, तो आपका ADL1 और ADL2 वो जनरेट हो गया। ये देखिए ADL1 लिखा हुआ है 45 माइनस 30 और ADL2 से दिस इज 15 और 30 आपका ADL मैट्रिक्स हो गया। That quickly you can generate this. वहां पे क्या था, कभी आप जो है ना यूनिट लोड मेथड अप्लाई करते थे डिस्प्लेसमेंट फाइंड, कभी कंजुगेट बीम के लिए आप एफर्ट्स को देख ले, कंजुगेट बीम बनाना, उसके एम और ई आई डायग्राम को उसके ऊपर लेट लोड करना, फिर करस्पॉन्डिंगली आप देखते थे कि आप अगर स्लोप मालूम, रोटेशन मालूम कर रहे हैं तो आप क्या करते हैं, शेयर मालूम करते थे कंजुगेट में। अगर आप वहां पे ट्रांसलेशन, तो ट्रांसलेशन के लिए आप उसी सेक्शन पे जाके आप मूवमेंट मालूम करते थे। सो देयर वी वर हैविंग सो मच एफर्ट। यहाँ पे क्या है, फिक्स्ड एंड एक्शंस तो आप दिए हुए फार्मूले से जल्दी से आप मालूम कर सकते हैं। कुछ समझ गए आपके नहीं?
Yes, sir.
दिस इज वेरी इजी एज कंपेयर टू दी फ्लेक्सिबिलिटी मेथड। तो ADL1 और ADL2 आपका जनरेट हो गया। अब नेक्स्ट में हम क्या करते हैं, टर्न बाय टर्न अब आप क्या करेंगे, आप रिलीज करेंगे, वहां पे रोटेशन अलाउ करेंगे और स्टिफनेस मैट्रिक्स जनरेट करेंगे। तो फर्स्ट हम क्या करते हैं, लोकेशन 1 पे हम यूनिट रोटेशन देंगे करस्पॉन्डिंग टू D1, और फिर करस्पॉन्डिंग टू D2 हम अलाउ करेंगे। 1 पे आप लोग अलाउ करेंगे तो आपका S11 और S21 मैट्रिक्स विच विल बी द फर्स्ट कॉलम ऑफ द स्टिफनेस कोएफिशिएंट मैट्रिक्स, वो आपका जनरेट हो जाएगा। और फिर आप करस्पॉन्डिंग टू D2 आप यूनिट रोटेशन देंगे तो आपका सेकंड कॉलम ऑफ द स्टिफनेस कोएफिशिएंट विच विल बी S12 और S22 जो है वो आपका जनरेट हो जाएगा। सो हियर नाउ यू सी हियर एट 1 हम क्या करते हैं, ये थीटा इज इक्वल टू 1 अप्लाई करते हैं and we apply the member and actions। अब आप कह सकते हैं कि हमें तो करस्पॉन्डिंग मोमेंट वैल्यूज यहाँ पे चाहिए, हमें तो करस्पॉन्डिंग ये एक्शन चाहिए, तो ये आप क्यों दे रहे हैं? बाकी मैं इसलिए कैलकुलेट कर रहा हूं, जब आप AML और AMD मैट्रिसेस पे जाएंगे तो यहीं से आप अपने वैल्यूज आप पिक करेंगे। आप समझ रहे हैं कि नहीं? तो एक ही लोकेशन पे जाके आप सारे मेंबर एंड एक्शंस वेरी क्लियरली एंड वेरी नाइसली यू राइट देम डाउन, सो दैट when you go after 2-3 pages, it should be easy for you people to collect those values and put them in for the calculation of the member and actions। अब यहाँ पे ये 4EI तो corresponding to D1 हम देख रहे हैं, तो इनका समेशन हम लेंगे। ये देखें, ये भी क्लॉकवाइज है, ये भी क्लॉकवाइज है, एंड क्लॉकवाइज इज आवर पॉजिटिव डायरेक्शन, सो 2EI थीटा और ये आपका 8EI थीटा हो जाएगा। ये S21 कितना होगा, 2EI थीटा। जब आप यहाँ पे अब आप आते हैं तो क्या, अब यहाँ पे क्या था, दिस वाज द जनरल इक्वेशन। यहाँ पे क्या हो रहा है, थीटा इज इक्वल टू 1 हम ले रहे हैं, तो वो थीटा वैल्यू जो है ना ऑलरेडी मल्टीप्लाइड बाय 1 हो जाता है, सो वी गेट दिस सैंपल विदाउट थीटा वैल्यूज। ये आपके करस्पॉन्डिंग आप L वैल्यूज हम डाल देते हैं। ये 12 कहाँ से आ रहा है, ये 12 इसके स्पेन से आ रहा है, ये 12 कहाँ से आ रहा है, ये इसके स्पेन से, सो वी गेट दिस वैल्यूज। फिर हम जाके ये देखें, S1 का क्या है, 4EI डिवाइडेड बाय 12, 4EI कंट्रीब्यूशन फ्रॉम द टू मेंबर्स। S21 का क्या है, 2E, तो 8EI ये हो गया। और इसका इसी तरह फिर हम क्या जाते हैं, D2 के करस्पॉन्डिंग हम यूनिट रोटेशन हम देते हैं, वी फाइंड आउट दिस। अब आपका S12 क्या होगा, इट विल बी 2EI थीटा डिवाइडेड बाय S22 क्या होगा, इट विल बी 4EI डिवाइडेड बाय L हो जाएगा, एंड वी राइट दीज वैल्यूज। ये अब आप देख रहे हैं 2EI ये हो गया, एंड विद दिस वी कंप्लीट ये आपका स्टिफनेस मैट्रिक्स यहाँ पे। इसके बाद हम क्या करते हैं, वी राइट द इक्विलिब्रियम इक्वेशन नाउ। अब सारे वैल्यूज तो है हमारे पास, ये वैल्यूज हम लगा लेते हैं, इसको सॉल्व कर लेते हैं, एंड इन टर्म्स ऑफ द EI वी आर गोइंग टू गेट दिस इक्वेशन नाउ। सो D1 D2 is equal to 0 and minus 90 over EI। D1 क्या है, 0 आ रहा है। इसके बाद हम मेंबर एंड एक्शंस पे आए, फर्ज कर सपोर्ट रिएक्शन हम मालूम करते हैं। मिडल वाला AS1 मैं कहता हूँ, राइट को हम क्या कहते हैं, AS2, एंड लेफ्ट एट सपोर्ट A we call this AS3। करस्पॉन्डिंग वैल्यूज जाके आप प्रीवियस डायग्राम से आप करेंगे, ASL ASD इंस्टेड ऑफ AML आई एम राइटिंग AS बिकॉज ऑफ सपोर्ट नाउ, और ASD AMD की जगह में लगा। अब आपके AS यहाँ पे था, दिस इज करस्पॉन्डिंग ASL नाउ। तो ASL क्या होगा, वर्टिकल समेशन ऑफ द वर्टिकल रिएक्शन कितना आ रहा है, यहाँ पे 15 था, यहाँ पे 10, तो आपका 25 हो गया। Why plus 25? Because this is in the same ASL1 direction, this is in the same, तो दोनों का अलजेब्रिक सम लेके आपका 25 हो गया। This was corresponding to, this ASL2 is corresponding to AS2 now, and how much is now the reaction at this 10? तो ये 10 यहाँ इसके corresponding हो गया. AS3 was at support A, तो corresponding value is 15 in the same direction, so we take this positive. ASL मैट्रिक्स आपका हो गया. अब ASD मैट्रिक्स कहाँ से बनाएंगे? यहाँ से बनाएंगे. ऑलरेडी ये था हमारे बिकॉज ऑफ द यूनिट डिस्प्लेसमेंट एप्लीकेशन करस्पॉन्डिंग टू D1. तो अब यहाँ पे आप देख लें ASD1 क्या होगा. ये दो जो आपके यहाँ पे रिएक्शंस आ रहे हैं इसका अलजेब्रिक सम लेंगे. तो हाउ मच इज दिस नाउ? दिस इज कमिंग 0 नाउ, प्लस एंड माइनस, सो द सेम मैग्नीट्यूड, दिस इज बिकमिंग 0. ये क्या होगा आपका? ASD21 कितना होगा? 6EI और 12 स्क्वायर, और ASD31 क्या होगा? 6EI. सो फर्स्ट कॉलम ऑफ द ASD मैट्रिक्स विल बी जनरेटेड. इसी तरह क्या करते हैं? करस्पॉन्डिंग टू यहाँ पे जाके हम कर लेते हैं D2 हम अप्लाई कर लेते हैं यूनिट, एंड वी फाइंड आउट. अब AS1D कितना होगा? इट विल बी -6EI डिवाइडेड बाय 12 स्क्वायर. ASD2 कितना? प्लस 6EI और 12 स्क्वायर, और ASD32 कितना होगा? दिस इज 0 नाउ करस्पॉन्डिंग टू दिस वैल्यू. Here now we put these values divided by L square किया हुआ है, and we complete this matrix. इसके बाद क्या है? D1, D2 हमने already find out किया हुआ है, so we multiply this and all the support reactions. Now you see here we just by putting this value multiplied by the joint displacements. When we solve this, so the support reactions are known. अगर आप कहते हैं कि नहीं मेंबर शेयर और मोमेंट्स भी हम इस तरीके से मालूम करते हैं, तो वो भी कर सकते हैं. देखिए आप पहले आप आइडेंटिफाई कर लें कि कौन से मेंबर एंड एक्शंस आप मालूम करना चाहते हैं. AM1 2 3 4 up to 7 आप देख लें. इसके करस्पॉन्डिंग वैल्यू आप AML के लिए ग्रैब करेंगे, AMD के ग्रैब करेंगे. ये ऑलरेडी है आपके पास 0 और -90, तो वही लगा लें. ये देखें आपके AML, तो ये करस्पॉन्डिंग टू AM1, करस्पॉन्डिंग टू AM2, करस्पॉन्डिंग टू AM3. सपोर्ट रिएक्शंस में दोनों हम ले रहे थे क्योंकि AS हम यहाँ पे सपोर्ट रिएक्शन तो इसका अलजेब्रिक सम, लेकिन आप इंडिविजुअली शेयर मालूम करना चाहते हैं तो इसी तरह आके आप क्या करेंगे? अंडर द एक्चुअल लोड जो आपके शेयर वैल्यूज यहाँ पे जो रिएक्शंस आ रहे हैं वही करस्पॉन्डिंग वैल्यूज आप पिक करेंगे. और ये है ऑलरेडी आपके पास एक्चुअल इक्वेशंस, एक्चुअल प्रॉब्लम से ये है आपके पास. इसी तरह अब आके आप AMD का फर्स्ट कॉलम कहाँ से जनरेट होगा? ये जनरेट हो गया. अब AMD का यहाँ से जनरेट हो, ये देखिए 6EI और ये हो गया, ये सारे 7 वैल्यू यहाँ से आप उठाएंगे. इसी तरह दूसरा कॉलम कहाँ से जनरेट होगा? जब आप D2 के करस्पॉन्डिंग ये वैल्यूज जो आ रहे हैं ये 0 हो जाएगा, ये भी 0 हो गया, ये -6EI, ये प्लस यहाँ पे 0 मोमेंट, यहाँ पे 0 मोमेंट, और ये आप इंक्लूड कर लेंगे. तो इसी तरह आपका AMD मैट्रिक्स वो जनरेट हो जाएगा. इसके बाद क्या इक्वेशन में लगा के आप मल्टीप्लाई कर लें, ये मल्टीप्लाई, तो सारे मेंबर एंड एक्शंस अभी आपके आगे. और ये देख रहे हैं +45 और -45. अगर एक मालूम करते हैं तो दूसरा अपोजिट डायरेक्शन में ऑटोमेटिकली मालूम हो जाता है. अब अगर ये दोनों मेंबर आप ये एंड शेयर्स आप जमा कर लेना तो वही आपका ये रिएक्शन जो आ रहा था S1 जो हमने कहा हुआ था वही आएगा. ये देख लें वहां से वेरीफाई, ये देख लें आप वेरीफाई कर सकते हैं. लेकिन I'll advise you not to repeat all these calculations again and again. ऑलरेडी आपने प्रीवियसली ये S3 और ये S2 के लिए मालूम किया हुआ है, so you don't need to come again and find and verify these things because you will be losing time now by doing all these calculations. इसके बाद आपके सारे मेंबर एंड एक्शंस है, आपका एक्सटर्नली लोडिंग है, आपका शेयर फोर्स डायग्राम कैसे बनेगा, आपका बेंडिंग मोमेंट डायग्राम कैसे बनेगा, तो वो नेक्स्ट में आ रहा है. दिस इज द रूटीन मेथड. तो इंशाल्लाह नेक्स्ट क्लास में आप क्या करेंगे? व्हेनेवर यू आर सेटिंग टू द नाउ this lecture, you should be sitting along with your pen, along with your pages, and then along with your calculator like you used to do it in the actual class. कुछ चीजें हम वेरीफाई करेंगे, कुछ आप कैलकुलेशंस करेंगे अपने इंटरेस्ट के लिए, और मैं आपको कह दूंगा, so this will become your class activity also. So from next onward, I can go to the screen and I can ask a particular person that you give me now this verification के आप verify कर लें। इसके बाद हम एग्जाम्पल 2 पे आएंगे जिसमें आपके रोटेशंस और सेटलमेंट्स इन्वॉल्व होंगी जिस तरह हम फ्लेक्सिबिलिटी में करते हैं। और ये देखें अगर ये ओवरहैंग पोर्शन आप लेते हैं ना तो 3 डिग्री तो यहाँ से आ गया, 2 डिग्री यहाँ से, दो अगर एक्सियल इफेक्ट्स भी हम इसको इग्नोर कर लें तो क्या होगा, 1 डिग्री यहाँ से रोटेशन, 1 डिग्री यहाँ से रोटेशन और 1 डिग्री यहाँ से रोटेशन और एक वर्टिकल ट्रांसलेशन, तो 4 डिग्री बन रहा है ये प्रॉब्लम हमारा। लेकिन हम क्या करेंगे, स्मार्टली हम इसको रिड्यूस करेंगे 2 डिग्रीज इनडिटरमिनेट प्रॉब्लम को, और इस ओवरहैंग पोर्शन को हम क्या करेंगे, इसका इक्विवेलेंट इफेक्ट हम यहाँ पे लेंगे। फिर इसको आगे ले जाके हम क्या करेंगे, हम कैसे स्मार्टली इसको एज ए 2 डिग्रीज इनडिटरमिनेट प्रॉब्लम सॉल्व करेंगे, तो वो भी हम डिस्कस करेंगे। सो दिस विल बी योर सेकंड प्रॉब्लम। सो राइट नाउ यू शुड बी हैविंग द कॉन्फिडेंस नाउ कि ये वैल्यूज हम, अब आपका क्या होगा कि आप क्या करेंगे, यू गो बैक नाउ, यू कंपेयर दिस मेथड विद द फ्लेक्सिबिलिटी। काइनेमेटिक इनडिटरमिनेसी क्या चीज है, हम स्ट्रक्चर को काइनेमेटिकली डिटरमिनेट कैसे बनाते हैं। इसके बाद आप जाके क्या करें, इसका एडी क्या है, एडीएल क्या है, फिक्स्ड एंड मोमेंट्स हम कैसे मालूम करते हैं, फिक्स्ड एंड एक्शंस इंस्टेड ऑफ मोमेंट्स, आई शुड बी सेइंग फिक्स्ड एंड एक्शंस, क्योंकि आपका वर्टिकल रिएक्शन भी हो सकता है। वो हम स्टैंडर्ड केसेस जो हमारे हैं, स्टैंडर्ड केसेस क्या है, यूडीएल अगर लगा हुआ है, आपका पॉइंटेड लोड अगर सेंटर पे हाफ सेंटर आ रहा है, ट्रायंगुलर लोड है आपका, अगर कपल विद इन द स्पैन है, इसको हम कैसे करते हैं, तो ये आप करें। फिर अगर हम एक एंड पे रोटेशन देते हैं तो उसी एंड पे कितना मोमेंट जनरेट होगा, कितना रिएक्शन जनरेट होगा, फार एंड पे कितना मोमेंट, उसका डायरेक्शन क्या होगा, मैग्नीट्यूड क्या होगा। अगर आप ट्रांसलेशन देते हैं तो इसके मेंबर एंड एक्शंस कितने जनरेट, कैसे जनरेट होंगे। तो और ये ऑल स्टेप्स जो है ना आपके काइनेमेटिक इंडिटरमिनेसी, मेकिंग द स्ट्रक्चर काइनेमेटिक डिटरमिनेट, स्ट्रेंथ स्ट्रक्चर जिसको हम कहते हैं। फिर एडी मैट्रिक्स कैसे मालूम करते हैं, एडीएल मैट्रिक्स कैसे मालूम करते हैं, स्टिफनेस कोएफिशिएंट मैट्रिक्स कैसे, फिर जाके हम इक्विलिब्रियम इक्वेशंस कैसे सॉल्व करते हैं, फिर सपोर्ट रिएक्शंस कैसे मालूम करते हैं, और मेंबर एंड एक्शंस। सो इट्स अ लॉट ऑफ वर्क नाउ एंड इट विल कीप यू बिजी फॉर द होल वीक नाउ। So next time, inshallah, when we come on the same Monday, 11 o'clock, we should be solving these 3 problems in detail. And I'll be asking you to verify all these values. ठीक हो गया?
Okay, sir.
Any question now? Okay,
Okay,
thank
sir.
you. Thank you so
No,
much
sir.
then. Okay, have a good time.
Thank you, sir.
Okay, bye-bye.
Director. Director, salah.
फिर से
सर जी लाने
Shooting मिलेगा.
Salati walgari.
हालात
Amir se chikka kara.
इधर चिक्का.
आया क्या ना बड़ा दास्तान है शोर हो गया यार
Tingga. Ada ka Bashir tawa video an ka kana.
हमें का बशीर वीडियो आन करे भाई.
क्लास के
Motai motai
हाँ د تاسو ویډیو ولې نه ځان کړی دا ویډیو لګان کوي دا مشاهدین نه کوي
ما وینه کنه
محمد ثابت الشوافي
څه وایي چې زه
او کم نه
بېدرالو
అలాగా సమాచార దాం కులే యార్ सर लगे बस के होइल नो बस लाड़ा बेचारा दान को कुमेल सर बले ओ apa tu
wow laalo sir
हेलो फहीम
ka فوجي مش فوجي
اه فهيم دی فهيم زما په خیال بس صرف آنلاین کړه دی بیا ته تللی دی
فوجي سره
kana salat kerja
समझो कि रोके जा रहे वहां
हेलो पानो अयो
انا
Alagano sahala pitra wani
خیر خیریت ته امن ده توای समझो कि
mara bas yaar walla kala
څنګه
मैं बस कल सुनो मैं शुरू को ما خيار د مستبشر ګرام ته دا غاستر کو
مړه سټرکچر خو نه دا بخینه زده کیږي
او کنه والله چې پر خپل پېنه او چې ته وایي چې ځان سره پېنه او کپی راوړې نیکسټ کلاس کې
نه زه حیران یم چې د کمباین سټډي نه بغیر ودا کو څنګه یار موږ دا خپل عادت وو
بعد یونیورسيټي تر غلې ما چې ته आवाज سټډي نه دا کړې
یاره خو کمباین مو خامخا سره غلې आवाज خو ځان ته نه کیږي او نو مسړې به پیږي کده څه وایي
نه مړه आवाज سټیمنا مونږ نشته 15 منټ هم نشو کې ناشته
او کنه بس دا کې سره او تیوري په بس دا باندې کړه ځان نو کې الله دا سټرکچر ته موږ
والا بس څنګه پر اگست ده او یونیورسيټي کولاو کې دا کا بس
دا ریکارډینګ چا شروع کړه دا ریکارډینګ چا شروع کړه هه بس ته کنه
ریکارډینګ وسه پوری دا افغان نه کوي افغان موجوده ښه خو ده شو دا والله وګوره
اخکاری خدا سے
والله وته او بشیر پیګی نه کوي دې خبره یوازې نه دی آنلاین دا پیګی پینا لګي
دا بشیر پیدا راز ده آی تھنک چې نمبر یې په وای
او بدا خبران دا نام په کله دا څه په باندې دا
څه شي
نام په کله ودا مې
یاره پته نه لګي دا خو چې فلاس ویک کې بینو
وایره بس په دې کې کوم دوه څه خالي فائنل بیا خسته وکړه وای
او مړه واز مېډ چې سکپ کړو دې ځله ټول فائنل کړو
والله بس خو
پکار دی نو کولاو کې
نه نه څنګه چل دی زره کا
څنګه چل نه و اسه ز خپل ویم کنه ویم چې دا مېډ ته خوا کړو بس پورا 100% کا مطلب
نه نه میډیکل دی تاسو دی
لاست ویک کې جون لاست ویک کې
نمبر خوده ته ګره یار
او کنه دا خو دغه د ایکسپیکټډ دی لاست ویک کې
کنفرم دی
او کنفرم دی دا غرض دی کی وی دي
مړه دا څه ول دي سړیا دا موږ سٹارټ هم نه دی راځي
سٹارټ پرې دا ته مونږ کلاسونه نه برابر کړی دي نو ته خدا والله
او کنه ما
کمیونټي تړولې دي خو بس د یونیورسيټي نه ته موړې نو مطلب چې هر څه کولاو کړل خو بس دا دې کولاو کی کنه
او کنه مړه مې هغه ټول یو اختیاري ته د دې په ما کې بل شي هغه صحیح فالو کولای شي
او مړه بس تینا بغیر نه کیږي ځکه چې دا خو پته سو پوری
او بل خبر ده چې ټرانسپورت چې کولاو چې ټرانسپورت وګوره څومره زیات مثال ټرانسپورت کیږي مختلف خلک ملويږي سره
ट्रांसपोर्ट कोलाओ दे टूरिज्म कोलाओ दे बिजनेसेस टूल कोलाओ दे मड़ा यो बस देते चल जोड़ कड़ा दे
او کنه بس ټرانسپورت نه خبره ده چې ټرانسپورت کې مختلف خلک کې هغه کې بیمار په باندې بیمار شته